So hello guys, welcome to this video. So in this video we are going to talk about transforms. Okay, and this video is like half an hour long. Okay, uh, you can see the length of the video. Okay, and basically this video will cover uh, almost everything about transformers mentioned in the paper. Attention is all you need. Okay, that was the paper that basically gave out the idea of transformers to the world. Okay, it was released by the folks at Google. Okay, so I hope that you will enjoy this video. Okay, it took a lot of effort to create this video. It took almost a month to create this video, uh, writing all the like slides content, preparing the slides, writing basically what to like speak about, and uh, like creating footnotes for each of the slides, and basically shooting and probably like reshooting some of the like parts. So it has like took some amount of effort. So I hope that you enjoy this video, and uh, I hope that you also learn a lot from this video. Okay, so just enjoy this video. Just try to like uh, learn something new from this video. If not the whole video, just try to learn something new from the video. Okay, and I would highly recommend that you watch this while having some probably like uh, pen and paper, because you might need to create some notes and all, because this video will create a lot will like create a lot of uh, ideas about new things and all. So you need to have that with you. Okay, so I hope that you enjoy the video. So let's just get into the video. I have everything prepared, so thank you. Let's start. So hello guys, welcome to this video. So today we are going to talk about transformers, and basically what are transformers. We are going to discuss that, why transformers were introduced and all of those stuff. So today it is going to be basically a discussion around what is transformers and its architecture and everything related to it. Okay, so basically just to like excite you about this video, in order to like make you stick to the end and to like learn more about transformers. So basically if you don't know what transformers are, basically transformers are the heart of all LLMs. Okay, so basically what are LLMs? LLMs are basically large language model. Okay, now what do I mean by large language model? Large language models are basically the chat GPT that you use, or maybe Claude. Okay, or maybe Gemini. Okay, so all these are basically what? All these are large language models. Okay, so basically any kind of AI chatbots that you are using, all of those are LLMs, large language models. Okay, so basically transformers are the core of this large language model. Okay, so basically like in your lower grades you must have like heard that basically the human body, in the human body or any organism, basically what happens is that the cell is the like building block of the body. Okay, like basically it is the core of the body and sort of like that. Basically without the cell the organism or the body cannot exist. Correct. So that's like I would say kind of a similar analogy for transformers also. Okay, so without transformers these large language models cannot exist. Okay, and we are going to also talk about how these were basically introduced and why they were introduced, and why only transformers did the job that it did, and why not something else. Okay, okay, now moving on to when the transformer was introduced. It was basically introduced in 2017. It was introduced by a research team at Google, okay, and it was released in a research paper known as Attention is All You Need. Okay, you can go through the paper. You can probably visit this link and go through the paper. It is a very nice research paper, and I promise you that by the end of the video you will get at least maybe 60-70% of the uh, content written in the research paper. Okay, so I promise you that if you stick till the end of this video and then you visit this uh, research paper, the original research paper that introduced transformers to the world, you will be able to understand 60 to 70%. Okay, and what I recommend you doing is that don't just read it once, maybe read it twice or thrice. Okay, and another thing that I suggest is use ChatGPT or Gemini in order to help you in the parts where you don't understand. Or another thing is that I provided my contact details also in the video description, so you can basically contact me, or even you can like leave a comment on the video. Okay, so you can go through this paper. Okay, so yeah, now why do we need transformers? Okay, so what is the reason that we need transformers? Okay, so if you don't know much about machine learning or deep learning or AI ML in general, okay, uh, so I recommend you to first go and first like maybe watch a video on LSTM RNN. Basically just get a hang of it. Basically just you can even like ask ChatGPT about what LSTM RNNs are, because if you don't know what LSTM RNNs are, then it's like not very helpful for me to teach you that why do we even need transformers. So there is like uh, no point in explaining you the need if you don't know what LSTM RNN is or how it works. I don't want you to like maybe watch a full-fledged 10-hour course on top of it. I just want you to have a basic understanding of it. I'll still try to explain you just a few things. Okay. Okay. So what LSTM RNNs are basically, it is the, okay, first let's unpack what the word stands for. So LSTM, okay, the word LSTM basically it stands for long short term memory. Okay, this is what LSTM stands for. Okay, and what the RNN stands for is basically recurrent neural networks. Okay, so basically this is what RNN stands for and this is what LSTM stands for. Okay, now what LSTM RNN is basically, first of all you basically need to know what an RNN is. Okay, if you don't know, like if you don't know what a neural network is, basically a neural network you can think of like it is how our probably our brain works. Okay, just to give you an example, a neural network kind of looks like something like this. Okay, there is, let's say, these three neurons. Okay, then there are two of these and then two of these, and this is connected to this and this and this and this and this and this and this. So this is what, this is a neural network. Okay, so what are neural networks? Neural networks are basically, you can think of them as the structure that helps us to that helps the like AI models to learn. Okay, so this is like you can say the core of the model. Okay, okay, you can even like research on it, like search on it on YouTube, just to like give you a very good resource. There is a good resource. Okay, I'm just gonna note it here. The channel name is 3 blue 1 brown. Okay, a lot of the content that I put up on my YouTube channel regarding AI ML and stuff, it is heavily inspired from this particular channel, the 3 Blue Brown. So you need to definitely check this out. Okay, you can learn about neural networks from this channel. Okay, and you can even, if you want, you can even learn more about this recurrent neural networks. But just to give you an example, like just to explain to you in short, basically what the recurrent neural networks did was basically, like you can think of them as basically, first of all, what before recurrent neural networks were existing, what happened is that basically in order to like train these neural networks, they did not have some kind of memory. Okay, they did not have any kind of memory to fall back into. Okay, so in order to like generate essays, or maybe in order to like do math calculations, so you need some kind of memory, because the model needs to store the input some way so that it can refer to that input and then it can generate some output based on that. So before all that, it did not have some kind of that I would say mechanism. But after this LSTM RNN, that was like brought into existence, and it was brought in around 1997, in the late 90s. And basically the job of it was, as you can like guess from the name, long short term memory. Okay, so let's unpack this one by one. First, the memory term. Okay, just like I said, memory is required so that it can store the context of the input. Okay, now what is this short term? So short term is basically, let's say I am looking at this particular sentence, the boy is playing. Okay, let's say I'm looking at this particular sentence. Now I want to train my LSTM RNN based on this sentence. Okay, now what happens is that basically, how do I train this? So how do I train this is basically, in order to like train this, I just told you that the model needs to have some kind of memory regarding this. Okay, some kind of memory. But what does the short term stands for? So let's say that if I am probably at this word, okay, let's say I'm at playing, so I need to have some kind of memory regarding the words near it, or you can say the words that are in shorter distance to it, or basically you can say that I should have some kind of short term memory. Okay, like just imagine this example. Okay, let's say that you have a 300 word essay that you have to read. Okay, now just think of this. Okay, if you are reading from the first word till the end of the whole essay, in the first read you won't be able to basically remember the whole essay. Correct, that is true. But what you can do basically is that, let's say your basically what was your task is, you need to read from the first word till the 300 word. Correct, now what, this is your task. Now what happens is basically, let's say that you went till the 105th word. Okay, now what happens is that basically when you are around this word, you won't have much memory about the first word. Okay, you won't have much memory of the first word. But what you might have is, you might have the context of the maybe 140th word. Am I correct? So this is what, this is short term memory. Okay, so you remember things that happened in a small duration ago. Okay, so that is what short term memory is. Okay, okay, so we have unpacked the short term memory, but what is this long? Okay, so in order to like have more context, so basically this is what it enables us to do. It enhances this short term memory. It is long. Basically you can say that you have huge or like much larger short term memory. Okay, so this is what an LSTM RNN is. This is very far-fetched like explanation of LSTM RNNs. There are much more things to know about it. You have to know all the gates in the LSTM RNNs, basically how it processes the context, how it remembers context, how it deletes context from its context window. You have to remember all of this. You have to like learn about what hidden state is, and all those stuff about LSTM RNN. So highly recommend you that you go to this particular channel and you search for LSTM RNN or any of the favorite YouTuber that you want, and then you can learn about this more. Okay, so LSTM RNN was existing before transformers. So what happened that it gave us the need for transformers. So what they did is basically they lost information in long sentences. Okay, now this is a problem with the LSTM RNNs. So basically you can see that there is no scope for long-term memory here. Okay, we do have long short-term memory, but it is not long-term memory. Correct? Am I correct? This is just what? This is long short-term memory. This is not long-term memory. So what happens is that, let's say this is just a 4-word sentence, but when I'm dealing with a 300-word essay or maybe 30,000 word essay, in that case, when I'm in the 30,000th word, I won't have any context in relation to the first word. And that is a problem because the last word might point to some reference in the start of the essay. That is very likely to happen. Okay. So in that case, I will lose all the context in long sentences. Okay. In long inputs. So that's where the LSTM RNNs were lacking. Now, this problem was solved by the attention mechanism. Okay, so I explained to you what LSTM RNNs are in this slide, but I won't be explaining you what attention mechanism is in this slide because we have a separate slide for that, which we will basically explore later down the line. Okay, but just to like give you an basic intro, basically what attention mechanism did, I'm just going to like give you an intro to what it actually helped us to do. So basically what it helped us to do is that they solved the issue of the LSTM RNNs. Okay, they solved the issue. And what was the issue? It was that they lost information in long sentences. Okay, they lost information in long sentences. So attention mechanism solved this. But there was another problem with attention mechanism. Okay, and what was the problem? They could not scale. Okay, by scale what I mean is that right now you know that the ChatGPT that you use, it has probably like maybe I think 500 million users, I think. So just imagine 500 million people using the app, using the ChatGPT app, using the ChatGPT models at the same time. So just imagine what amount of scale they require in order to achieve this. Okay, their model needs to be ultra efficient, their model needs to be super fast in order to handle 500 million concurrent users. Of course they don't have 500 million concurrent users, but probably it would be in the range of maybe 50 million or 100 million. Okay, so that's why scale is important. But this attention mechanism, it did not provide a scale. Okay, and how it did not provide a scale is basically it could not handle parallel processing. And let me tell you guys, transformers are a genius at parallel processing. Okay, we will learn something known as multi-head attention, which helps us basically in parallel processing. Don't get scared, I'm just throwing these words out in order to like excite you a bit, not to scare you. Okay, so this is the reasons that gave rise to transformers, which was, as I already mentioned, was introduced in 2017 by researchers at Google. Okay, and as I mentioned, it can handle very long sentences, very long sentences, and also parallel processing. Okay. Okay, so now we know that why do we need transformers. Okay, now let's actually go to the working. Okay, now let's actually find out that how does the transformer actually work. Okay, so now we are actually going to talk about how the transformer actually works. Okay, so before starting off the working of the transformer, let's first understand the parts of the transformer. Okay, so basically there are multiple parts in a transformer. Okay, there are maybe 10-20 parts. Okay, if you just go through this diagram over here. Okay, this diagram, so this is the architecture of the whole transformer, and as you can see there are multiple parts. There is this thing known as input embeddings, then this multi-head attention, feed forward, and a lot of the parts are basically, as you can see, repeatable. Okay, correct. So our goal in this video is to basically break down this whole architecture into as simpler parts as possible. Okay, so basically my goal is to teach you all of those small parts, and then we will combine those parts, and then we will understand the whole working. Okay, so that way anyone can grasp the whole knowledge of this video. Okay, let's now move on to, yes, so basically before moving on to each of the tiny parts, we first need to understand two big parts of the transformer, like two main parts you can say. The first one is the encoder, the second one is the decoder. Okay, the encoder is the thing that you see over here. Okay, let me show you. So the encoder part is this. Okay, and basically this is the decoder part. Okay, and I have taken that same diagram over here also, as you can see. Okay, so basically if we just read about encoder a bit. Okay, it is very simple. Okay, I have made all the notes very simple for you. Okay, first of all, what the encoder does is basically it reads and understands the input. Okay, like this is a very far-fetched like you can say far-fetched way of saying what actually encoder does, but it is a very simple analogy of understanding what a encoder actually does. Basically its job is to understand the input that you are giving to the model. Okay, breaking down the context of the input, understanding the context of the input, basically understanding the structure of the input. Let's say that you have let's say you give chat gpt and essay. Okay, okay, you give chat gpt an essay and you tell it to summarize this essay. Okay, so what the encoder does is basically it is responsible for reading that essay, making sense of the essay, making sense of the structure of the essay, like what are the, let's say it's stories of some ancient time. So basically it will make sense of the characters, who are the characters in that particular story, who are the what are the characters doing and all, and how is the story carried out, what is the conclusion of the story, all of that, so that decoder can take over, and then it can generate the output that you as a user want. And what do you want? You want a summary of this essay, correct? So the decoder will actually take the understanding of the encoder, and then it will build on top of it. It will build what? It will build the, or you can say a more correct term would be, it will generate the output on top of the what? On top of the encoder. Okay, so that's basically a very far-fetched way of understanding encoder and decoder. You need to go much deeper into these. As I have already mentioned, you can watch out 3 blue 1 brown channel. It is very good in these matter. Or you can even like ask me, and I'm happy to make another video particularly on this topic only. Okay, so as you can see, if we read the notes, it's exactly what I said. It basically captures the relationship between each word and it creates the context vectors. Okay, so this one is very important. What are the context vectors? We will talk about them in just I think 1 or 2 slides ahead. So just wait a few minutes. We will be talking about what are context vectors in very great detail. Okay. If we move on to decoder, so what it does, generates the output sequence one token at a time based on cross attention from encoder and masked attention from itself. Okay. Now basically I have tried to keep all the notes as simple as possible, but also at the same time I've tried to made it a little bit theoretical, so that even if you are lazy enough to not maybe refer to other external resources, even if you just refer to these notes, you can still somehow appear smart in other in front of other people, or in your interviews, or any sort of thing. Okay, so that's why I've included some buzzwords right now. But let me tell you, we will cover what is cross attention, what is masked attention. We will cover these later down the line in this video only, so don't worry about that. You can just keep this marked at this time. We will be learning about it in just a few I don't know the exact minutes, but yeah, you will come across this very soon. Okay, so now I hope that you know what a encoder is and a decoder is. And basically now our task is to first go into the encoder, and then basically learn about each of the parts of the encoder. And then our job is to basically go into the decoder and then learn about each of its part. Okay. And the good thing is, basically, as you can see, a lot of the parts in the decoder and the encoder are basically repeatable. As you can see, this input embedding, output embedding, they are repeating. This multi-head attention is also repeating. It's just that it's masked. We will also learn about what multi-head attention and what masked multi-head attention is. Okay. As you can see, this add and norm layer is also repeatable. This feed forward is repeatable. Okay, there is only two new things, not two, actually three new things. First of all, the masked one, then the softmax, and then linear. This is the three things that is extra in the decoder, which you don't find in the encoder. But we will cover everything. Okay, don't worry. Okay, so our first of all, let's go step by step. Okay, so our first task is to basically cover this part. Okay, this input embedding part. Okay, so let's now go into that part. Okay, so basically in this part we are going to talk about tokenization and embedding. Okay, what was the layer known as input embedding? So we will not just learn about what is embedding, we will also learn about what is tokenization. Let me tell you, these are not same. Okay, these are not same at all, because I've heard a lot of times people saying that they use this both of these terms interchangeably, but let me tell you, they are not same. They are totally different. And in this video I will clear your every doubt you have about these two words. Okay, you will clearly get the the difference between these two. Okay, so first of all, let's talk about tokenization. Okay, let's just first of all see that why is tokenization or even embedding is needed. Okay, so why is it needed? Okay, let's read this out. Okay, machines don't understand hi or hello. It is correct, right? Your machine, probably the laptop that you're watching this video right now in, it can't understand the text or the voice messages that you send it. It cannot understand that. What it understands, it only understands zeros and ones. Correct? Yes, you know this from very lower grade classes. You might be even knowing how to convert the texts into binary, or even you must be like knowing numbers to binary. Yeah, so they can only understand numbers. That is correct. Specifically, not just any number, just zeros and ones, binary. That is why tokenization and embedding is required. Okay, so now our goal is to basically what? Our goal is to, let's say, I hi I say something to like this to my, let's say, my laptop. Okay, so I say something like how hi oh, sorry, I've written, oh, just leave it, how are you, to my laptop. Okay, so how do you think my laptop will react? Okay, so the answer is it will not react. Why? Because this text that you are seeing, this is readable by humans. Yes, because you can read it, it is readable by humans, but it is not readable by laptop. Okay, or for that matter any machine in the world. So you have to somehow find some way in order to convert this into numbers, correct? Because laptops are or machines are basically good with numbers, correct? Specifically what? Binary. But if you know just a bit basics about binary, you must be knowing how to convert numbers to binary. If I like give you an example, like how would you convert 56 to binary, you can easily do it, right? It's not that hard. So our goal is to basically just convert the text we have into number. Rest of the process is easy. Okay, the conversion of binary numbers to binary is easy. That process already exists. So we somehow need to find some way in order to convert the texts, into numbers, correct? So what is that way? That way is known as tokenization plus embedding. Because tokenization directly doesn't convert the text into numbers. Okay, it does the part of the job. You can say 50% of the job. The rest of the 50% of the job is carried out by embedding. Okay, we will also talk about that also. Okay, now let's read the definition of tokenization. Okay, let's just read this. Okay, then we will break down the definition piece by piece. Okay, so what is the definition? The definition is the process of finding and matching patterns in the input string and breaking them down into tokens. Tokens are what? Chunks of the original string. Now let's understand this with the help of an example. Okay, so we have this example. Okay, so what does this example say? This is the same one over here. How are you? So let's say I give this to my laptop as we were already talking about. So how do I convert this to numbers? So the first step is basically in this text over here, you need to actually find out some patterns. Okay, now how do you find these patterns? Okay, so in order to find these patterns, okay, there are multiple algorithms. Let me tell you, there are multiple algorithms. Okay, in the research paper which I was talking about, this Google one, they have used I think they used an algorithm named as BPE, byte pair encoding. So basically we will not go deep into what this algorithm, how this works. We will only look into how like just the basics of the algorithm. Okay, we will just look into the basics of the algorithm. Don't worry about it, you will be able to understand it. Okay, so why do we need patterns? Okay, because, okay, let's say that you are given a very big problem to solve. Okay, so what is your approach? Do you solve it in one go? No, right? You tend to basically divide it into much smaller problems. Okay, and how do you break it? Do you break it randomly? Okay, no, right? You don't break it randomly, you find some kind of pattern, right? If I say that Okay, let's take a much better example over here. Let's say, so let's imagine that I have this pizza over here. Okay, now let's say that you are a person who works at a pizza cafe and your job is to divide this pizza. Okay, your job is to basically divide this pizza. So how do you do it? Do you randomly cut pieces? Do you just cut over here, then over here, then over here, then over here, and just make a big mess out of this pizza? No, right? This is not what you do, correct? Instead, what you do is something like this. So let's say this is the pizza. What you do, you first cut over here, then over here, then over here, and lastly over here. So this way basically you have not made a mess of the pizza, correct? So this is what, this is correct. Okay, you don't use this, you use this method. Okay, now what is the difference? Why did we use this method to break the pizza and not this method? The answer is this has some kind of pattern. What is the pattern? The pattern is basically you just keep breaking the pizza down into halves. Whatever the pizza is left, you just keep breaking into halves, and then you reach the like the amount of pizzas like in a very uniform manner, correct? So that is a pattern that you are following. Do you are you following a pattern in this one? No, right? So what is the key in this? Basically pattern. Just a second. Oh yes, yeah. So basically patterns are very important. As you can see, we use pattern over here, so we get a very good result. We did not use pattern over here, so we got not good results. Okay, so that's why you can easily remember this analogy of why do you need to find patterns in order to break something down into simpler pieces, correct? So our goal is to basically take this text and break it down into simpler pieces. So we need to find some kind of pattern in this. Okay, and how do we find that pattern? Okay, let me explain the BP algorithm just a bit. Okay, so what it does is basically let's take the example of maybe, okay, so this sentence is very you can say very small in order to explain the algorithm. So I'll take the example of, let's take the example of maybe this one. Okay, let's take the example of this one, this sentence. Okay, now let's read the sentence and try to find some kind of pattern. So what the pattern like how the BP algorithm finds the pattern is basically you go through the whole sentence and then you try to find some strings of word, substrings of word actually, which are repeating in the sentence. Let me find you one. Okay, if you go over here and if you check, the ing is repeating a lot of times. It is repeating over here, it is repeating over here, it is repeating over here, over here, and over here also. So it is repeating how many times? 1 2 3 4 5, correct? So it is repeating 5 times. So what this BP algorithm will do is basically it will convert this ing. Okay, it will convert this ing with something that is not present in this string, or something random that doesn't make sense to this string. So it could be something like, let's say, z. So after this process, what will happen is basically, let's say we are talking about this word. Okay, this is what this is, finding, right? So how will it get convert? Basically find. Okay, till here it is good, but after that what will happen is that this ing that you see, it will get converted to z. Okay, so that's how it finds pattern and then basically it replaces them, and then it will do this recursively. What do I mean recursively? It will do this till there are no more patterns to be found. So this is basically how the BP algorithm works at a much higher abstracted level. Okay, and how does this help? Okay, let's take the example of this. Okay, so basically this tokenization that you see, this is like this algorithm, how it works, like I just explained you, this does not work during the training of the transformer, because let me tell you, the tokenizer that we use, it is already trained on a large set of text, on a large corpus of text. So we don't train the tokenizer at the moment that we are training the transformer. So it already knows the pattern, it already knows what patterns exist, and it just breaks down the sentences. Okay, I hope you understood what I just said. Basically what happens is that the transformer is not training the tokenizer at the moment that the transformer is training. No, what happens actually is that the tokenizer is already trained using this algorithm. Okay, and what happens is that basically this tends, like this gives rise to the tokenizer already knowing the patterns. So when the transformer is getting trained, it just doesn't train the tokenizer. Instead what it does is it just breaks the sentences, breaks the strings, breaks the texts into simpler parts using the patterns it already has learned during its own training, not the transformer training phase. Okay, I hope you understand this fully. Okay, now let's take the example of this. Okay, let's say I said how are you. So using some pattern, we don't know really what pattern it is following or not, but let's say that it divided it into 4 chunks. Okay, the first chunk is basically HO, then there is WAR, then the third one is EYO, then the fourth one is basically U, and then the question mark. Okay, so let me tell you, you must also be thinking, you must have like thought from first principles that why are we doing this technique? Why can't we just basically convert each of the word into separate tokens? Wouldn't it be like very like easy to do? So that is just a small homework for you. You can basically Google it or use ChatGPT or any YouTube video. I just want you to find that answer for yourself, because in that way you will learn a lot. Okay, but if you don't find, you can still comment on the video and I will I'm happy to explain to you. Okay, so this is how basically the string is divided into tokens, or basically chunks of the original text. Okay, this is first chunk, this is second chunk, this is third, and this is fourth. So these are what? These are, you have learned a new word. These are what? These are tokens. Okay, okay, so now we know what tokenization is, how it works, we know what tokens are basically. Okay, so let's not try to read the definition one more time, and this time you will understand it completely. So the process of finding and matching patterns, okay, that was already done. Right now we are just not finding the patterns, but we are just matching the patterns, correct, in the input string. Okay, in the input string, and breaking them down into tokens. So 1 2 3 4, 4 tokens. So these are what? These are tokens, and tokens are basically what? They are chunks of the original string. Okay, so I hope you understood everything about tokenization. If you want, you can read more about it. If you want, you can even read more about BP. There is this very genius name as Andre Karpathy. You can search him on YouTube. Basically, he worked in OpenAI and Tesla also. So he's a really genius person, and he had also made a video on BP algorithm. Basically, he created a he, like he did all the coding himself. He coded the like the BP algorithm from scratch in order to build his own tokenizer. So you can watch that video. It is really good. I think it's like, oh, 2 or 3 hours long. Okay. Okay, so now we have understood the 50% of the like process. So what was our original goal? Our original goal was to basically take any sort of sentence and then convert those into numbers. But what is the progress till now? We have been only able to convert it into tokens. So our next job is to basically take these tokens that we have and convert them into numbers. As simple as that. Okay. So embedding is that process only. It is just taking these tokens and just converting them into what? Into separate numbers. Like this HO got converted into 206. This got converted into 89. Okay, this one got converted into 143. This got converted to 109. And when you take all these like all these numbers together, what do you get? This is what, if you have uh, learned anything about vectors and all, you have recognized by now this is what, this is a vector. Okay, so let's just read the definition one time. So the process of converting the tokens into meaningful vector representations. Okay, meaningful vector representations. We are going to talk about what we actually mean by meaningful. But let's first understand the vector representation part that we have already understood. Actually, you just saw that, okay, this is a vector. How did we get? Basically, each token got converted into different set of numbers, and then we combine those, then we get the vector. So that is a vector representation of the tokens, correct, which are then passed to the model for training or inference. Okay, very simple. Okay, now what do I mean by this meaningful vector representation? Okay, so what do you think that uh, okay, like we talked about that how the tokenizer, or basically the tokenization process that we talked about that the tokenizer is already trained, okay, in order to match the patterns. Okay, it has already found all the patterns, it is now just matching the patterns. So don't you think it is important to also do some kind of similar process with embedding also? Yes, it is very simple, it is very much needed, because if let's say I enter some number over or some text over here, sorry, some text over here, and the same text, when I enter the next time, I get some other number. Okay, very like huge difference in those numbers. So don't you think that is just like the embedding that we are doing, it is just randomly doing it? No, I mean, yes, right, it is just randomly doing it. So that would cause the model not to learn anything. It will cause various errors in the model, because the model will not able to understand that, okay, the person is trying to say this, because every time the numbers that is getting generated from the text are different. So it is not able to actually understand the original text. Okay, do you get my point? So that is why this embedding is also important to be trained. So that's why it is trained already on a large text. Okay, and it basically gives us meaningful vector representation. Now I think you must know what do I mean by meaningful. Meaningful in the sense that it should be some, it should have some meaning to the transform model, correct? If it does not make any sense to the model, the embedding is not good enough. So that's why we need to have some meaningful vector representation. Okay, You can research more about embedding and all. It is a very huge field. Okay, a few things that you can basically research about. If you want to know more about this, you can learn something known as vector db. Okay, over here there are some known as pinecone, Fires. There's, I think, Supabase also provides it. Yes. Okay. Uh, then, okay, let me not teach you this. Let me just give you another like small concept to remember for you. Just a little off track. Okay. So why do we represent, or why do we like, not why, what do we mean by meaningful vector presentations? I'm just going to talk about it a bit more. Okay, so why do we even need vectors? Okay, so first of all, we already spoke that we need some way of converting the text into the numbers. So those numbers are basically these vectors. And why do we need them to meaningful? So that the order, so that the model actually basically have some meaning of the text. It can basically not be confused of the text. Okay, so that's why it is important to have some meaningful vectors. And how do we actually make those meaningful vectors? So basically, let's say that let's say you have two words. There is this king and there is this queen. Okay, now one thing you must be knowing, that whatever vectors that you are talking about, they can be represented in a graph, correct? If I'm talking about, let's say for example, I'm talking about this vector, let's say 5 I cap plus 7 j cap. So what this basically means is that in terms of x, in the x direction it stretches till 5 units, and in the y direction it stretches till 4 units, correct? This is what I mean by what? This is what I mean by a vector, correct? This, if you see, this basically is it stretches in this much in the first direction, first dimension, in the second, in the third, and the fourth. Okay, so this is how vectors work, correct? Now let us imagine that we convert these into vectors. Let's say the king that it comes out to be, it is, let's say, 2 3. Okay, and we don't know what the vector of the queen is. Okay, but let's just guess it. Okay, let's draw the graph. Okay, so let's say this is the graph. Okay, so if you see this king, the king will be somewhere. If you see this 2 3, it will be somewhere over here. Okay, not, let me just write it as king. Okay, if you know this is the first quadrant, this is the second, this is the third, this is the fourth quadrant. Am I correct? Yes. Okay, now what do you think if you just look at these two words? Okay, the king and the queen, they are very different in meaning, correct? So do you think that if I plot the queen's vector, will it be in the first quadrant? No, right? Because it is in very opposite meaning. So it should be somewhere around in the third quadrant, right? So it should be somewhere around over here, correct? And let's say we do get something like that. So in order to do this, I think yes, both will be negative. Let's say we get something like this. So it will be somewhere over here only, correct? So this is meaningful, right? Now let's talk about something else. Okay, some other word. Let's talk about man. Okay, now what do you think? Man is more similar to king or more similar to queen? Of course it is more similar to king, correct? So what happens? the man vector should be situated where? Should it be situated in the first quadrant, in the second, in the third, or the fourth? One thing it is clear that it should never be in the third quadrant, because man and queen are not at all related. Okay, second or fourth and first, let's choose between these three. So what do you think? Man is really close to king. Okay, so it should be of course in the first quadrant, correct? So this time also we see that it is in the first quadrant. Okay, so this time the vector that we get, it might be something like this. You can see it is very close to the king, it is very far from the queen, correct? So as you can see, this like, okay, we as humans mentally know that man is closer to king, man is closer not closer to queen, king is absolutely opposite of queen. Okay, we know this, but for machines it is not that easy to know this. But if you see, if we use this method to basically represent the words in vectors, and then basically have this kind of representation, this kind of meaningful representation, don't you think that using this representation the machine will be so much intelligent? It will be nearly as intelligent as knowing about these things as us humans, correct? So this is what I mean by meaningful vector representations. Okay, so I hope that you have understood what embedding is, what tokenization is. Okay, now we will move on to the step 2. Okay, okay, so let's now move on to the step 2. Okay, so now we are going to talk about positional encoding. Okay, so what is positional encoding? Okay, this is the step 2 in our journey. Okay, so let's go over it step by step. Okay, so till now what we are able to do, okay, we are able to take text and convert them into numbers, correct? Yes, we take text and convert it into numbers using what? Using tokenization and embedding. Okay, now just think about this particular example. Okay, like if I have some sentence, okay, like let's say the boy ran. Okay, so what do you think? Like, or let's just leave this example. Okay, we'll take a much better example which we already have in our next slide. Okay, let's take this example. Okay, let's take these two sentences. Okay, now if you see the first sentence say that lion ate the tiger. The second sentence say that tiger ate the lion, correct? Now do you think that position of the words, or basically order of the words, is important? Yes, it is important, because you see in this example this implies that the lion ate the tiger, but this sentence implies that the tiger ate the lion. So just by changing the order of just two words, which are lion and tiger, we get a whole new meaning to the sentence, correct? So don't you think that the order of the words is very important? So what we have implied till now, that we want some kind of order. Yes, it is very important, right? Because if we don't have order in our sentences, it is going to be very like confusing for the like model to learn, or to even like make sense of the sentence. Okay, if I just change the order a little bit, the whole meaning of the sentence will change. Okay, so it is very important to know the order of the sentence. Okay, so that is why we need positional encoding. Okay, let's just read this out. As humans, we can easily understand the order of the words in a sentence, correct? We just read the sentence sequentially, like word by word, and we understand the order of the words. Okay, correct? But for machines, it is not that easy to remember the order. Okay, but machines can't actually remember that lion in the sentence lion came before tiger, or ate come before the. In the sentence, it doesn't know that lion occurs after tiger. Okay, lion is the fourth word in the sentence, or any kind of like information, the positional like meaning, it doesn't have that. So positional encoding helps us achieve that. Okay, now let's read the definition. The process of adding positional meaning. Just now we talked about this. Okay, this is very important. What do we want? We want positional meaning to our input sequences, correct? These texts by manipulating the vector representation of the input. Okay, now this is also very important. Like, how do we do it? Okay, how positional encoding is done, or what does positional encoding actually means? So it means like the basic thing, the basic definition could be like manipulation of the vector representations of the input. In this input, basically what I mean, the text. Okay, so that is how basically positional encoding occurs. Now, what do I mean by actually this definition? That how do I manipulate the vector representations of the text? Like we just saw that this is how you represent the sentences in terms of vectors. Okay, but how do you manipulate this? Okay, so that we are going to see in like in this section. Okay, so what could be one way to do this? Okay, let's just take this example. Okay, let's say we have this one. Okay, or let's take just some other one. Okay, let's take this one, 1 2 3 4. Okay, let's just say that or yeah, let's just take this example. Okay, we have this vector, we got this from this sentence, let's say. Okay, so we got the vector of this whole sentence, not this whole sentence. Okay, let's just say that we got this vector from just the word the. Okay, and for the word boy, let's say we got something like 10 20 50 60 maybe. For the word ran, we got, let's say 55 69 33 22, let's say. Okay, let's change this a bit. Okay, just a little bit. Okay, so 11 12 3, now let's make it 13 and 44. Okay, so we have these three vectors over here. This is the vector for the, this is the vector for ran, and this is the vector for boy. Okay, so one thing we can do is basically we can just add a new dimension to the vector, which is actually denoting the order of that particular word in that sentence. Okay, by order of the word in that particular sentence, what do I mean? If you consider this sentence over here, okay, let me rewrite it over here. The boy ran. Okay, if we see this sentence, what is the order of the in this sentence? So think about it in terms of like the array indexing that you do. You know that in array indexing it starts from 0, then 1, then 2. It doesn't start from 1. So we are going to mark this position as 0. Then next one, boy will be 1 and ran will be 2, correct? So what we do is basically we just add a new dimension to this vector. Okay, and how do we do that is basically we keep the old vector as it is. Okay, and we just add a new value. Okay, which is going to be what, the order of that particular word in the whole sentence. Okay, so what is that? It is 0. Okay, so we add 0 over here, correct? Now if we do the same for let's say this one is boy, correct? So if we do this for boy, what it will become? It will become 10 20 50 60, and at last it will add 1, correct? So this become this. Now if we talk about what will the vector of ran become? It will be 55, 69, 33, 22 as it is, and at last 2. Okay, so as you can see, we have got 3 new vectors over here. Okay, this one, and this one. Okay, so basically this is the new vector of the this is the new vector of this is which one? This is boy, and this is ran, correct? Okay, so we have got some new vectors over here. Okay, now if you see, these vectors have some kind of positional meaning to this, correct? Because if you see right now, I can basically say that, okay, basically just consider the vectors till the last dimension. Okay, and the till that last one. Okay, but don't consider that last one. That last one is just denoting the position of the word. Okay, so we have built a, you can say, very glitchy, very hacky method of positional encoding. Okay, but it works right now. Okay, in our 3-word case it is working, but let me show you an example. So that's why I made a separate slide on this in order to explain to you, because a lot of you, even I, thought of this same approach. Okay, when I was learning about positional encoding for the same first time, but this does not work, this does not scale, and we need scale for transformers. Okay, so we need to solve this issue. So how do we do that? Let's go over this slide over here. Okay, so why can't we use indexing? Okay, like I have showed you that like what is the meaning of using indexing for positional encoding. Now you know what positional encoding is all and stuff. Okay, let's read this out again. Let's say our vector is this. Okay, 24, 109, 92, and we want to use indexing to store the word by just appending the current position to the vector. For example, for position 12, it will become this. Basically what happens is that, as you can see over here, okay, just a second, as you can see this word over here, okay, this vector over here, it is 24, 109 and 92. So it is the same till here, and the position is just getting added. Okay, as you can see over here. Okay, so this is what we did just a few minutes back over here, correct? So let's now read that why we don't need to do, or why we don't do this. What is the problem with it? But what if our number of words is in the range of hundreds of thousands? Then such huge number will cause errors in the accuracy of the model prediction and training. Okay, let's see this very nice example that I drew out for you guys. Okay, let's look at this. Okay, so first of all, what do you have? You have this position, the word, and the vector with position. Okay, okay, let's now first go with the word. Okay, the word that we are basically looking at, the particular word that we are looking at in the sentence. Okay, so the first one is the, then it is lion, then it is 8. Okay, so for the position is 0, and this is what we get as the vector, and this is just we are adding the 0. As you can see, the same is with over here, we are just adding what, 1. Okay, the same is with here, we are just adding 2. Okay, we are just what, we are just applying tokenization into the words, then applying what, applying vector, like embedding, and then basically we get the vector, and then we just append the position to the end of the vector. That is what we are doing, correct? Now let's say that we have this many numbers, so it is like some 2.8 lakhs number of words. Okay, and that word is basically this xyz, and let's say this is the vector of that particular word. So do you think that, what do we do now? So we are following a particular basically pattern that we are doing over here, correct? So we will do what, we will just
add this to, we will just append it to the end. So as you can see, this will become something like this, correct? But now you see this particular number, it is way too large, correct? It is just way too large. Okay, so that's why these large numbers are not good for training. Okay, they're not good for training the transformer. Okay, they are not good for the model. Okay, now why they are not good for the model, and basically what errors they cause, you can research more about it. Okay, there's a particular topic regarding this, vanishing gradient. Okay, you can basically research about this particular topic, that what vanishing gradient actually means, or you can even like search on YouTube or anything, that why neural networks, or basically these AI, like why neural, just search that why neural networks can't handle very huge numbers. Okay, you will get your answer. But let me just tell you in short. Basically what happens is that, let's just understand it this way. Okay, let's say let's draw it over here, I guess. Yeah, let's say that you are um, um so how can we like say this? Okay, just like take for example, okay, that you have some kind of tray. Okay, and in that basically you are doing what, you are basically collecting, okay, you are basically collecting some cookies on it. Okay, and then basically you are delivering those cookies. Okay, so you are doing what, you are basically first collecting the cookies in this tray, and then you are basically delivering it to somewhere else. Okay, let's take this very simple analogy. Now let's say the cookie is of size, let's say 10 into 10 centimeter. Okay, but now let's say I come around and I just give you a cookie that is like, it's not actually possible to make such big cookie, but let's say I give you something like 2000 into 2000 centimeter cookie. So now just let me like, just let me know that, do you think that this huge cookie, would it be like feasible for you, or would it be even possible for you to carry in this tray? Because your tray is made to carry these small cookies. Okay, you can carry hundreds of these cookies, or maybe like tens of these cookies. Maybe you can carry like, let's say 50 cookies of size 10 into 10 centimeter. Okay, but what you can't do is basically you can't handle this very big cookie. Okay, you can't handle this very big cookie in the tray, because your tray is not made to handle such a big cookie, correct? Your tray is made to handle these cookies. So what will you do, you will have some problems in basically digesting this, or maybe you can say more proper word would be ingesting this. Okay, so it won't be possible for you to have this cookie in your tray. So you can't actually take this cookie in your tray, and that is a very big problem. So we need to make sure that our cookies are somewhere around this size. It can be smaller, that is no issue. Okay, the basically cookie size can be way smaller than this. Okay, it can be like 1 centimeter also, that is very valid. But it can't be like more than this, or even very higher than this. Like 20 centimeter is also okay, 100 centimeter also okay. Let's for one instance just say that, okay, 100 centimeter is also okay, but this 2000 centimeters is just too much. Okay, it is just like how many times, it is 200 times this size of the particular cookie. So it is just too much. And as you can see, the numbers that you see over here, okay, it's 24, 100, 90, 100, 40, 12, 30, 15, 60. So all in the range of like less than 100, you can say. Or even if they are above 100, it is not very huge than 100. So you can say probably like the numbers range from like 0 to 120. Okay. Now you have the capacity of handling this much cookie, which is what, 0 to 100 numbers, correct? But what I am doing is that I am giving you such a huge number. Okay, I am giving you this number to handle. So do you think would you be able to handle this? Of course not. So that is why basically the model cannot handle these very big numbers. Okay, so that's why this is like not a knowledgeable explanation of it. This was just to like explain to you in like so that you actually remember this. But you need to actually research on this, and I've told it multiple times that you can even comment it down and I'll reach out to you. Okay, so now I think that you know that why don't we use indexing for positional encoding. What is positional encoding? Okay, so what do we actually use in, if we don't use indexing, what is the method that we use? Okay, so this is basically the formula that we use to calculate our positional encoding. Okay, now this looks very complex to you. It should look complex. It is complex, but we are not going to break down this whole formula. Okay, we are just going to look at it like just a small like explanation, like just a small intro. Okay, this formula deserves its own probably like 20-30 minutes video of its own. Okay, but just to like give you like an example of how it basically works, or just the intro. Okay, so we calculate the positional encoded vectors in some way, in something like this way. Okay, let's say we have something like 10, 15, 18, 3 and 7, let's say. So we have this particular vector that we want to apply positional encoding. Okay, so how do I convert this vector into some vector that basically has positional meaning? Because that is our main goal, correct? So how do we do that? We use this formula that you see over here. Okay, this formula is actually the formula that they have used in the paper of attention is all you need. This is the same formula. Now there are multiple ways to do positional encoding. This is just one way of doing it. There are multiple way. You can, if you want, you can even search it on ChatGPT. Okay, now just like have some look into this formula. Okay, so how do I calculate this? So first of all, like this is what, this is pos, as I have written here. It is what, it is the position of the current word. Okay, so if we take the example of 10, the pos will be what, the pos will be 0. Okay, the pos will be what, it will be 0. Okay, now what is I is basically the current index of the vector. Okay, so basically in this case the I will be also 0. Okay, now how is this happening is that basically, let's just see this example. Okay, now let's say that my original sentence was lion ate the deer. Okay, this is my original sentence, and this vector that you see over here, it is actually just the vector of lion. The word ate, the word the word deer will have very different vectors, as you can see over here also, correct? So this is just the vector of the lion. So that's why the position of this vector that you see, its position is 0. Okay, because the position of the word is what? 0. What is I then? So basically I is the index of the vector. What do I mean by index? So basically the index of 10 will be a 0, then 1, then 2, then 3, then 4. Okay, so what is basically this index that we are talking? So this is 0, this is 1, this is 2, this is 3, this is 4. So that's why what we are getting the I as 0 over here and the position as 0. Okay, let me just show you another example. If we go to 15, the position will be what? The position will be still be 0, but now the I will be what? 1. Okay, if we take some other like vector of the word, if we take the vector of 8, in that case the position will be what? 1. The position of the word deer will be what? It will be what? 0, 1, 2, 3. So it will be 3. Okay, so you have no now you know that what is pos, what is I. Now there is another variable into this. Okay, this is what? D model. Now what is this D model? This is just the size of the vectors, that's it. Like the size of the vectors over here is what? In this case this is just constant. Okay, this is what? This is 5. Okay, for this one it is constant, for this every vector it is the same, because we are maintaining the order of the size of the vector, so it is always going to be some constant number. Okay, and in this case it is 5. Okay, in the research paper I think it is 64. Okay, okay, that is for another conversation. Okay, okay, so now let's just look into the formula once more, now that we know all the variables. Okay, so basically you have these two formulas. Okay, so this is this, like if you you use this formula in the event terms and you use this formula basically in the odd terms. By even and odd, what I mean is basically this actually relates to how these sine and cos functions are and how they actually look like graphically. So that's why they have this particular formula. Okay, so you don't need to like go deep into how this whole formula works. Okay, you can just take a look from far away and understand it. Okay, because you know that how it's actually calculated. Okay, now let's just see what the result will something look like. So what it will do is that basically it will calculate some PE value. Okay, some positional encoding value, and then what we need to do is that let's say that for this 10 that we got, let's say the positional encoding we got is let's say 8. So we just add this particular value to the original vector. Okay, to the what? To the original vector. So it will become what? It will become 18. Okay, and then like this we will be calculating for this and just add it to this, and just like that all the vectors will stay the same size. Okay, that is very important property, you should remember that the vectors size stays same. Okay, that is a very important property. Okay, so you should remember that. Okay, so this is how this whole vector will be converted into something like this. Of course this will have some else value and it will be basically added to it. There are a lot more operations on this. You can actually go through the research paper if you want. I can even, like, if possible I'll try to cover it in some other video if you want. Okay, okay, so this is how basically we calculate the positional encoded vectors. Okay, and the method that we are using, this is basically known as sinusoidal encoding. So this is basically known as sinusoidal encoding. Okay, so now we know what is positional encoding, why do we need it, what it is actually, and for that, why don't we just use indexing, and if we don't use indexing, what do we actually use, and we also actually looked into the formula a little bit. Okay, so I hope you understand this part. So now let's move on to the next part. 3, 2, 1, go. So now we are going to talk about self-attention. Okay, self-attention is the most important concept that you need to grab in this whole video about transformers. Okay, because the paper that we are talking about, the research paper that we are like so diligently following, that name, that research paper's name is attention is all you need. So there is a very keen focus on attention. Okay, so in this part of the video we are going to cover that, like what really is self attention, what are we paying attention to, and why is it so crucial. And we are also going to cover the parts like why basically transformers are considered to be like working in parallel, and why they are considered to be so faster than the previous mechanisms. Okay, like the previous LSTM RNNs and attention mechanism. And the thing is that in the paper attention is all you need, they have mentioned attention, but it is not a concept that was introduced in that paper. It was actually introduced by a group of scientists led by Yoshua Bengio. And Yoshua Bengio is basically, you can say, he's the godfather of deep learning. Just like there is another godfather of machine learning, so Jeffrey Hinton, right? And there are a lot of people who have like contributed like that. So attention was not like given in this paper, but it was the very, you can say, key part of everything that transformer is doing. So that's why we need to pay very much attention to this attention. Okay, so what is self attention? Let's first read the basic definition that I have written over here for you guys. Then we'll cover it like end to end. Okay, don't worry about it. I have all the steps written down over here. We are going to take an example. We are going to cover it very clearly. Okay, so what is self attention? It is the core functionality of a transformer and is responsible for finding the relationship between each word in the sentence. I've already established that it is the core functionality of a transformer. Okay, we will also see that how is it basically responsible for finding the relationship between each word in the sentence. Because at the end of the day, the transformer is what it is, like working with language tasks. It is doing language related tasks, right? Language related tasks are like first of all, when this transformer architecture was actually introduced in the paper way back in 2016 or 2015, basically what they intended to do with this was basically they wanted to build a translator. I guess it was from French to English or vice versa, something like that. And basically that's what the language task they were hoping to accomplish with this architecture. But later down the line, a lot of AI researchers and a lot of people in the industry, they realize that this technology is not just limited to
using in translators, it should be like used in other language related tasks also. And just forward a few years, in 2021 I guess, or 2022, ChatGPT was launched to the public, and it worked brilliantly. Of course, the first versions of ChatGPT was not very good in tasks like writing essays or something like that, but down the line they improved it. But the thing is that it all comes down to language related tasks. Now, right now it is not just used for language related tasks, because transformers are also used in vision related tasks also. Those type of transformers are known as VIT, which is basically vision transformers. And basically they are used almost with the same architecture that we use for the language tasks, but uh, uh, like accompanied with CNNs and a lot of things. Okay, we are not going to go into all of that. I'm just accomplishing the fact that the transformer had a sole objective of working with language related tasks. So in order to understand language, you need to understand how words are related to each other in a particular sentence, right? As a human being, if I say to you that, okay, go and bring me the bottle of water, so you, as a human being, you are very much able to like understand this particular sentence, because it is not that difficult for you, because you understand the words that are related to each other in this sentence. Go and bring the bottle of water. So I'm saying that go and bring. Bring what? Bring bottle of water. Bring bottle of what? Bring bottle of water. So you're very well able to understand that how these words are interlinked with each other. You very well know that go and water bottle is not that interlinked. It is not having any link, but you do know that bottle and water is very much related. It somehow can be used interchangeably also, right? You know that because as a human being, you know how words are linked with each other. So if we want a transformer to work just like us, we need something like that, so that they can also understand what the relationship between each word in the sentence. So that is what self attention helps us to do. Okay, so basically each word can compare themselves with all the other words. This is the core of what self attention means, or attention means. Okay, basically all the words compare themselves with each other, and that's how we find the relationship, and that's how the transformer builds a sense of the words. It builds a sense of grammar, it builds a sense of creativity, like writing essays. It builds a sense of probably doing math, anything. That's the basic core that we are talking about. Okay, so there are three core parts in attention. Okay, the first one is query, the second one is key, and the third one is value. Okay, so we have three of them: query, key, and value. Okay, now query is basically, as the name suggests, what do you think by query? Like you must be having some query related to this video, so you post a comment on my video, so I written back to you. And please do that if you have any query. Okay, so you must be understanding what query is, right? It is like asking some question if you are looking for some answers. Like basically you are looking for some answers, right? That is what a query is. So basically, what is a query? What am I looking for? It's very simple, right? What is the key? We are in this context, we are not looking to the physical key. We are looking we are looking at basically what is the, you can say, what kind of feature, or what kind of behavior, or what kind of you can say what kind of things that I'm providing. That is what key. Okay, like basically I am like, okay, I can offer you these services. Okay, so this is what key is. Okay, like these are my key services, these are my key offerings. So that is what do I offer. Okay, now the third thing is value. What info do I pass along? Basically, what is my name, uh, what is my age, what is my gender, where do I live, and other things like that. That is the value. Okay, you can basically think of those as like basically uh, okay, let me explain it to you over here. You must have heard of something known as JSON, right? JavaScript object notation, right? JSON is what? JSON is like a technique, or not technique exactly. It's just a data type, you can say. Basically, it's just a kind of way to store data, right? To send data here and there in servers, right? So how is it basically written? You have seen something like this, right? That okay, I am saying that user, and then his name is, let's say, Sayantan. Then age is, let's say, 20, and then I'm closing this. Okay, so this is JSON, right? I'm going to remove this part. Okay, just this part. This is JSON, right? So you must be knowing that in this name thing, what do we call it? We, just a second, we call this as key, right? And over here, what do we call this? We call this value, right? This is very simple notation that we use in JSON. We even use this in dictionaries in Python also, right? We even use this in dictionaries, right? In Python, right? You must have like seen some kind of this. We have also used in objects and all. So in dictionary, it is like very well used in Python, because you must have like heard that key value pair. Okay, dictionaries in Python are key value pairs, right? So what is this key? This key is, okay, this thing that I am looking at, this data that I am looking at, it is offering me name. It has name. But what is the name? That is the value of that particular key, right? That value is Sayantan. So this data object, this data actually is giving me name. But what is the name? It is Sayantan. It is giving me age. That is the key. But 20 is the value, because it is the actual value that I'm getting. So I hope now you clearly understand the difference between key and value, right? Very easy to understand. God has made things in a very sensible manner. So someone who created JSON might have probably inspired the person naming these key and value thing, because they are exactly the same. Okay. Now, I hope that you understand what is query, what is key, and what is value. So now let's take an example of why did I actually teach you these three things, and how do they actually help in like attention mechanism, and what are we actually talking about. Okay, it will make sense with this particular sentence. Okay, so the sentence is, the boy is running for the past 1 hour. Okay, the boy is running for the past 1 hour. Okay, let's read this out. For the above sentence, let's say we want to see the queue of running. Then it will look through the sentence that who is actually running. Okay, nice. So what is the queue? This queue thing, what is it? So queue is basically, it is querying about any particular word. Okay, what did we learn is that basically words compare themselves with all the other words to find the relationship between them. So basically if I take this particular word which is running, and what I'm doing is I'm comparing it with the, then I'm comparing it with boy, then I'm comparing it with yes, then I'm comparing it with running also, I'm comparing it with for, then the, then past, then one, then are, right? So what I'm doing is that I'm comparing with all the words, and what I'm doing is that I'm trying to find the queue of this, the query. Okay, now the query is basically who is running, who is running. Okay, I can see that the word is running, but who is actually running? So I will find that the boy is actually running. Okay, so that is basically how I finding my queue. Okay, now let's read this more. For the word boy, its K will be that he can run, and its V will be that he can run for 1 hour. Okay, very simple. See, the boy is basically having some key. Okay, that key is basically that he can run. Okay, and his V, which is value, is that he can run for past 1 hour. Okay, let's try to relate this with our example of Jason, shall we? So let's just take this example that I have something like this, that let's say run um, one, let's say 60 minutes, or let's just say I'm writing it as 1 hour. Okay, I have this particular JSON for the JSON data for the boy. Now as you can see, run is the basically what it is, the key. Then what is the value of this run? It is 1 hour, right? That is the V, that is the value, right? So basically by now you must have understood that key is something like qualitative, like okay, he can do this, but for how many times, for how much time, or how well he can do that, that is what V tells us about. Okay, so I hope that now you have a bit more clarity into what Q is, into what Q is, into what V is, and into what K is. Okay, now let us go through this example once more. Okay, that how did we actually use this KQV thing, so to like give like how much attention, or what type of attention that we are talking about. Okay, so let's just consider once again this word running. Okay, so this word running is basically it will query with all the words. Okay, that who is running, who is running, that it will first go to the word the, are you running, no, are you running, it will say yes, I am running. Now how will it see that the boy is actually running? How did it see that boy is running? Because when we are trying to find that who is running for this particular word, we are actually looking into the key and the value of this particular word, into the particular key of this particular word. Okay, and what is that? It is run. So we know that he can run. Okay, so my query is resolved. Okay, so when I am like putting some attention,
Okay, that how much attention should this particular word be putting to other words. That is what I am using this KQV values for, because you see, this word will running will put a lot of attention into boy because it is very important. Okay, it will probably, let's say, put 40% of its attention on boy. The rest of it, let's see, is not very that important. For is also not very important. But another thing is important, this 1 hour thing. Okay, this past 1 hour thing, these three words are also very important, because these words basically denote that how much for how much duration the boy was running. So it is also very important. And how will it find that it is important? It will once again compare its queue with the other case, and here it will see that this past 1 hour thing, it has a key which is basically run. Okay, because basically we are talking about this duration in the context of how much we are running. Okay, so that's it, that's its key. So that's how it will say that, okay, I need to put attention into this also. Let's say combined three of them, it puts, let's say, 40% of attention, and the rest of them it puts, let's say, the rest of the 20%. Okay, so that's how this attention, this word is putting attention into other words, and that's how we are forming the very basic language understanding. Okay, this way we are basically building the understanding of language, that how words are interlinked with each other, that how this word is very linked with this but not very with this. Just like the example that I gave you, that go and bring that bottle of water. Now if I like give that particular sentence to a transformer, so it will basically take the q, k and v, and then basically pass those value, pass those basically like do the attention thing for each of the word, so to find that how much important all the other words are for that particular word, just like we did over here. So that is how basically transformers use attention, and that is the attention that I am talking about, that we are talking about in this transformers architecture. Okay, so I hope that you now understand what is this self attention. Okay, what is this query, what is this key, what is this value. I hope you understand all of this. Okay, now we are going to talk about that how it actually works. Okay, let's talk about that. Okay, so there are a number of steps. Okay, there are a number of steps over here, so we are going to cover them one by one. Okay, okay, so the first step is we initialize the weights of k, k, q, k, v as identity matrix. Okay, now it might get a little bit scary for you that how did we jump into matrices now. Okay, I would very heavily like recommend you to watch a channel which is 3 blue 1 brown. Okay, you should definitely watch this channel, because it has a very nice visualization of this particular thing that I'm trying to like explain. He has explained it through a animation that was really cool and really awesome, and it was like really easy to understand also for beginners. So I will provide the link in the description, and I highly recommend you to check that video, because it is really helpful. It will like um, make you understand more about this. See, because the thing is, I am not going to like tell you to just follow my video, because of course my video, even if it is like 3 hours long or 5 hours long or 10 hours long, it will still not be enough. This field that we are working in, it is like changing
probably more than anything else in the world right now. Every day it is changing, and you need to be updated every day. The architecture that we are learning in this particular video of transformers, the truth is they don't even use that architecture nowadays. It is like something else now. Of course they use the fundamental parts, it stays the same, the fundamental building block stays the same, but the thing is that they have made a lot of changes on top of that to improve it, of course. So that is why you need to be like more updated with this. So of course, check out channels like Three Blue, One Brown. There is another channel, Andre Karpati. I would urge you to not go through all of his videos right now. Just the ones that you can find interesting or understandable enough, you can go through them. But he goes into a lot more coding, so you have to be like more hands on with the code before you move on to his channel. Okay, so let's come back to this. Okay, so before moving on to all the steps that how does it actually work, like how do we actually calculate that attention, how do we compare those words, I want to want you to show you another example. Okay, this is taken from the paper only, from the attention is all you need paper. Okay, and as you can see, this here is an example. It is a very long sequence, right? Let's try to like decode it, that what they are trying to infer from this, like refer from this particular example. Like if you can read basically what this sentence is, you need to like tilt your device a bit, or maybe tilt your head a bit to read this. It is saying that it is in this spirit that a majority of American governments have passed new laws since 2009, making the registration or voting process more difficult. Okay, and then there's this like full stop, and then there's this special token. I hope that you know what this means. Basically this means end of sequence. So basically that means that okay, this whole sentence is now over, the sequence of the tokens is now over. So that's what this EOS means. And then there's the padding sequences. Okay, we are also like padding this particular sentence, because in our in our transformer the number of tokens is fixed. It is 512. We are using that many number of uh, tokens to represent any sort of textual data. So that's why if the number of tokens is less than that number, then we pad it. Okay, uh, so that is what this padding does. Okay, now if you see, let's try to like read this. Okay, then we'll know that what is going on here. An example of the attention mechanism following long distance dependencies in the encoder self attention in layer 5 or 6. Okay, what do they mean by this is basically, if we go back a little bit, if we see over here, just a second, yes, over here in the multi-ed attention there is we are like doing self attention over here. So that is what they are talking about. Okay, that in that particular layer, this is what is like kind of happening. Okay, they are demonstrating that many of the attention heads attend to a distant dependency of the verb making. Okay, so basically they are showing that okay, this particular sequence of tokens that we have, what is the word making paying attention to. So as you can see, it is paying attention to 2009. It is paying attention to itself also. It is paying a lot of attention to more difficult, because it makes sense to say something like that, making more difficult. Okay, like it is like completing the phrase, making more difficult, making registration or voting more difficult. So making more difficult. So what happened is that in this particular sentence, now the transformer has kind of a knowledge that
uh, this particular bill or whatever this new law that they have passed, it is making more difficult. Now what is being made more difficult, it doesn't know that yet, but if it applies the this particular same attention mechanism to all of these words, then of course it will be very easily be able to assess that what is being made more difficult. But right now it can understand just from the word making that making more difficult. Okay, so attentions here shown only for the word making, they're not showing for any of the other else. But of course each of them are paying attention to all of the other words. Okay, and the word self over here means that only, because this particular sequence of token, this particular sentence, you can think of that way, each word is like paying attention to all the other words in the sentence, so that's why it is self attention. Okay, we will also talk about what is multi-headed attention. Okay, but now we can basically move on to like learn that how it actually works. Okay, okay, so let's see. So what is the first step? We initialize the weights of q, k, v as identity matrix. Okay, so we now know that what is q, what is k, what is v. Okay, q is query, k is key, and v is value. Okay, we now know that what these particular things actually mean. Okay, now why do we need weights of these q, k, and v? Because we do need weights for them, because basically you can think of this way that how much should I basically uh, basically this, like the attention that you see over here, all of it is not working like this way that we are seeing that. Okay, making should pay more attention to more difficult. Okay, it is not working like the way humans do. Okay, like transformer needs numbers to work with, they need some mathematical way, it needs some numeric method through which it can probably like assess that what amount of attention should I pay to any particular word. So that's why we need to have some weights for those q, k, and v, because like in a simple neural network also, if we have a very simple neural network like this. Okay, and basically something like this. Okay, so each of these neurons that you see over here, each of them have some kind of weight, right? If you know even little bit about machine learning, you must be deep learning, you must be knowing that each of these neurons have some kind of weights, right? So why do have they weights? Because we can basically change those weights, we can basically change the biases, and then based on that like basically I can because the thing is that each of the values passed through this neuron is being multiplied by that weight. So if I am like changing the weight, so I'm changing the weight in such a way that I decrease the loss. So that weight factor is kind of like you can say you must have seen something like when a DJ is like playing some music, he has this kind of device, and he has a lot of like buttons, or basically which he can like rotate, and the song's volume can be like decreased or increased, or he can basically mix two songs and all. So that is what weights are used for, like basically you are kind of like changing them accordingly, so that you can get better accuracy when you're like training. Okay, so that's what we are using the weights for. Okay, now let's see. Okay, so this is my weight of q. Okay, and then this is my weight of k, and this is my weight of v. Okay, now what we are doing is basically now we are multiplying q, k, v with the respective weight matrix. Okay, now we are basically multiplying q with wq, k with wk, v with wv. Okay, now you must be saying that okay, we did learn that basically this is our weights of q, k and v, but what is our q, what is our k, what is our v? That is a valid question, right? So what is our kqv? So the thing is, whatever dimension of the whatever 512 dimension vector represent representation you have created of the input, that is replicated as q, k, v. Okay, that is replicated as q, k and v. So basically you must have learned in this section, right, in embedding, that if we have a word like this, we basically encode it like this. So basically what I'm doing is that I'm taking this and I'm making it my q, my k and v, all three of them. Okay, now this is what this is just how much this is, 1 2 3 4 4 dimension, but in our transformer we have 512 dimension. Okay, and we are just copying them as q, k and v. Now you might have like got an understanding that like a hint on why these weights are so important, because the thing is when we are starting with the training process, this q, k and v are the same. Okay, they are literally the same, but they should not be the same. There should be some difference in them, because they mean very different in meaning with each other. Okay, so how do I make them different? That's what I do by multiplying these them with their respective weights. Okay, and don't worry, right now we have just taken them as identity matrix, but later down the line we will also like make them make changes to them. Okay, so that's why we need weights. Okay, and that's why we are multiplying the q, k, v with their respective weights. Okay, now next is multiply the q vector with all the other k vectors. Okay, so what I'm doing is I'm taking the q vector of that particular word and then multiplying it with all the other k vectors in that particular sentence. Okay, so let's take this example. Okay, so what I'm going to do is I'm going to come to this word, the, I'm going to take its q vector and then I'm going to compare it with the k vector of boy, then the k vector of is, then the k vector of running, then the k vector of for, then the, and then like this I will go on till the end of the sequence. Okay, so what I'm doing is basically, as you can see over here, what is query, what I am I looking for, what is key, what do I offer. So basically what I am doing is that basically I am going to each of the sentence, each of the word in the sentence, and I am looking that based on my query, who can provide me that particular answer. Okay, right now I don't yet know what the answer is, but I'm just looking for that who has the answer. Okay, so let's just say in our previous examples also, like if we are taking the queue of running, right, if we take the queue of this and run through just like we did with this, if we run through each of them, so it will have a very like good match with the basically it will basically look through that who it is running, who is running, and then it will find a very good match with the k of boy, right? So that is what is like basically happening in this particular step, and that is why we are basically uh, multiplying the q vector with all the other k vectors. Okay, you can think of this step as if the query is browsing through all the keys and then trying to get the best match. Okay, that is what is happening in this particular step. Okay, now what we are doing is then we scale down the value of the operation from step 3. Now whatever operation that we are getting from here, we are scaling it down. Okay, now what do I mean by scale down? Okay, let's read this a bit more. Scaling is done because if the values of the result is too big, then the accuracy of the model will decrease. Due to this, we do scaling by dividing the result by the square root of dk size of the q and k vector. Okay, so let's say my just a second. Let's say that my q vector is something like this, like, okay, let's have this q vector and another k vector. I have something, let's say, like this. So when I basically multiply this, I will get a very big value, right? I'm going to get probably a very big value, right? I'm getting this. So I have very huge values over there, right? Now why will this cause a problem in our like later down the line when we are training? Because mostly we are presenting the model with numbers like ranging from 0 to 1, right? Okay, but suddenly instead of 0 to 1, we are basically providing numbers like 200 or 1000. So the model will, like, let's say that basically you are like trained for a particular task of like you have a very small bowl. Okay, and you need to catch some tennis balls into that bowl. You need to fit some tennis balls into that bowl. So let's say that I give you 10 tennis balls, so you can probably fit them easily. You can fit them easily, right? But what if instead of 10 tennis balls, suddenly instead of that I give you like let's say just two footballs, then that would probably not working with you. Okay, if I, let's say, give you 10 footballs, then you won't be probably able to fit those 10 footballs into that particular bowl, because that bowl is not made for handling those many those big footballs. Okay, it can only like handle small tennis balls. Okay, so the neural networks can handle only those tennis balls. Okay, it can handle small numbers. It is good with small numbers, but when you give very huge numbers like those footballs, it will basically cause inaccuracies. It will probably give us very wrong outputs. So that's why we don't want that. So what happens is that we take this kq value, the multiplication of the q and the k, and then we scale down. Okay, how do we scale down? So as you can see, I have written it over here, that we basically scale down by dividing the result, which basically means qk, by the square root of dk. And dk is what? It is the size of the q and k vector. So in our case, dk is how much? Dk is 512. Okay, so what we will do is basically we take this value and divide it by root of 512. So it will become something like 200 will be divided by root 512, 1000 will be divided by root 512, 1500 also the same, and 350 also the same. Now after doing this, if I just do the math a little bit, let's just do it for just maybe one or two, just a second. So 22.62, just a second guys. So this becomes 8.84, then this becomes 44.2, this becomes 66.3, and this becomes 15.4. okay. Now as you can see, if I compare these values and I compare these values, you can see that there is a huge difference, because the numbers over here are very big. It is in the ranges of like uh, hundreds, and these two are in the ranges of thousands, right? But in this case, the greatest value is only like how much it is, 66. So it is, all the values are like in the range of 0 to 100, or probably like 0 to 50, a few like here and there. Okay, so that is why we do scaling. Okay, and how we do it, I've explained it to you. Okay, now what we are doing, we are applying softmax on the scaled value to get the attention weights. Okay, the attention weights helps us decide how much attention to give to each word. Okay, now what we are doing is we are applying softmax on the scaled value. So whatever value that we are getting from, after scaling this, whatever value we are getting, we are applying softmax into it. Now if you don't know what softmax is basically some kind of mathematical formula through which you can like convert a group of numbers. If I have something like a group of numbers, like I have 1, I have 2, I have 3, I have 4, I have 5. So if I pass all of these numbers through softmax, so it will give it these 5 numbers, it will convert it into group of probabilities. Okay, and why do I need probability? Because the thing is that I need to somehow convert these raw numbers that I have, because they don't make any sense. But if I am able to basically convert these raw numbers into something very like good, which is like probability, that how much it what's the like you can say probability in, basically it will be like converted into percentage. Okay, so basically if I see something like, instead of this I see something, let's say I see something like this. Okay, um, okay, so instead of this, if I see something like this, it will be like very easy for me to like assess. Okay, it will be very easy for the transformer also, because now you can see instead of these numbers, there are like solid you can say probabilities, or you can like say very solid like how much should I pay attention to the this word, or the word in this position, or the word in this position, or the word in this position. So I probably should pay attention to this one, right? And this is what we call as attention weights. Okay, this is what we call as attention weights, because attention weights are like, what do they do? They help us decide how much attention to give to each one. Okay, so let's just say instead of 512, I have just 4 in my like I'm using just 4 dimensioned vectors instead of 512. So basically this would what happened. So I should pay this much attention to the first token, this much to the second token, this much to the third token, and this much to the fourth token. So this is what's like happening. Okay, okay, so I hope that now you understand that what do I mean by softmax, and why did we basically applied softmax, and what are these attention weights. Okay, now what we are going to do is we are going to take these particular weights that we got and calculate the final attention scores. Okay, now we have calculated the attention score, attention weight. Okay, just like we had weights for the QKV, we have weights for the attention also, but we have not yet assessed the attention scores. So how do we do that? Is basically we multiply with each value vector. Okay, we multiply the attention weights with each v, basically giving required amount of attention to each word. Okay, so how do I get this? Basically I got this attention weights, okay, that I should pay this much attention to the third word. Okay, but what is the third word? Okay, I'm not going to just like multiply with its original you can say original vector form that we had created. No, because that is not very helpful. I need something what does that third word provides me. What we know it as is basically what we know it as value, right? So what value is that particular word providing me? Okay, and how much attention I am paying to it. Okay, so whatever value it is paying giving to me, and this is how much attention I should pay to it. And when I basically multiply these two, I get the final attention score, that okay, this much attention I should pay to this value that the token is providing me, and this is the final attention score. Okay, and based on that, the transformer will make sure that each word forms meaningful connections with the other words, and that's how basically this self attention works. Okay, and that is the last step. Okay, so I hope now that you understand that what do I mean by attention scores, and how did we actually calculate them. Basically we multiplied them the attention weights with each value vector. Okay, and why did we do that? Is basically we want to have the final attention score, and we have something known as attention weight, which basically gives us an idea of how much attention I should pay to each of the word. Now I need the content of the word. Okay, I need the value of the word, because I need to see that what value is that word providing to me, because I have the basically you can say I know how much value I should get from that word, but I don't know what value I am getting from that word. So the value of that particular word is giving me that. Okay, and I'm just multiplying both of them to get the final attention score for each of the word, with respect to the current word we are at. Okay, and this is how self attention works. Okay, so just to revise it, let's just go through it once more, because this is very crucial. If you understand this, you probably know the very core of transformers. Okay, so the step one is we basically initialize the weights of q, k and v as wq, wk and wv. Okay, and we initialize them as identity matrix. Okay, of course this is not going to be like 3 by 3. It is going to be how much? It is going to be of the size 512, right? Okay, next up, when then in step 2 what we do is basically we multiply the qkv with their respective weight matrix. Okay, and how did we get this qkv? We basically whatever vector representation we have created of that particular sentence, we just copy it as q, k and v. Okay, and basically to create difference between them, because basically we can't have them same because they mean very different. So what we are doing is basically we are having these weights. That's the purpose of these weights, because they will help us differentiate between q, k and v, and that's why we are going to multiply them with their respective weight matrix. Okay, Then what we are doing is we are going to take the q vector of that particular word we are currently in, and then we are going to multiply that q vector with all the other k vectors of the words. Okay, and why we are doing this is basically we are querying through all the words in that sentence, and then looking at that what are they providing us. Okay, and we are trying to get the best match for our query. Okay, then when we are doing this operation, there might be cases that the value that we are getting, it is like very huge, and it may cause issues with our training. So what we do, we scale down the value of the operation from step 3, whatever step we did of like multiplying q with k, the value of qk we scale down. And how do we do that? We basically divide qk by the square root of dk. In our case it is 512. And what is dk? It is the size of the qk and v also. Okay, and v vector also. Okay, then what do we do? Whatever we did over here, we basically apply softmax on them to get the like attention weights. Okay, why do we apply softmax? Because these are just raw numbers that we get, but applying softmax gives us probability. It gives us a sense of like how much percentage attention to give to this particular word or this particular word. And that's what we are going to use it in step 6 also. What do? We calculate the final attention scores by multiplying with each value vector, by multiplying the attention weights with each value vector. Okay, we multiply attention weights with each value vector, basically giving required amount of attention to each word. Okay, so I hope that now you understand how self attention works. And let me tell you, if you understand this, you probably understand a lot. Okay, you understand with the very core of transformers. And if you did not get any part of this particular section, I highly recommend you to rewatch it once, twice, thrice, or how many times it needs, like it requires for you to like get the full grasp of this topic, because it really needs your attention. Okay, self attention requires your attention very much. Okay, like, because this is the thing that makes ChatGPT or Claude or the Gemini. And like you see these Gemini and Claude and ChatGPT, and you probably like before watching this video or before like diving into machine learning or deep learning, you probably would have like wondered that how do they work? They seem like magic and all. Even I used to do that, but after learning all this, you can like feel that just doing this silly matrix multiplication that we used to do in probably like 7th or 8th grade, just doing that basically is has created something as beautiful as that, something as powerful as that. So just these small matrix of course these are not small, these are just 3 by 3, but we have like 512 by 512, so it is a lot. But my point, the point being is that basically these this self attention, it is such a concept that it still powers a lot of almost all the AI applications that we use in our day-to-day life. So I highly recommend you to go through this more. And as I have already mentioned, you should go through 3 Blue 1 Brown. He is a very great guy. He provides a lot of knowledge through animations and stuff. And I highly recommend you to watch his video, which I have like mentioned in my description, because it visualizes all of this self attention stuff in a very you can say visual manner. Okay, and after watching this stuff over on my this video, you can surely watch that, because I've provided, I think, like I've provided you enough to understand all of those stuff, and also enough for you to go through the research paper also. Okay, by the end of the video you can I would not say like you would like understand fully of it, but if you go through it, you will understand probably like 80% of it very nicely. Okay, because the paper is not that very difficult as compared to very many other papers. Okay. Okay, so there is a particular formula, okay, which basically summarizes everything that we have basically done over here from step 1 to step 6. Okay, what is that? Basically, we are multiplying q and k. Where did we do that? Q and k we are multiplying. Of course it is not showing all this because that is like being done before applying this formula only, and then we are basically scaling that. And how we are doing that? Basically dividing it by root dk. Okay, we are done doing that. Then we are taking the softmax of that. We are taking the softmax. Okay, this particular value is what it is, the weight. Okay, what? The attention weight. Okay, so we know all of that. Okay, right? So we know that this is the attention weight. Okay. Okay, so we have that attention weight. Then in order to calculate the final attention scores, we basically multiply it with v. That is what we are doing. We are multiplying this whole thing with v, and this is what we are getting the attention as. Okay, now just show this to someone who hasn't watched this video yet. It could be a friend, it could be a family member, or anyone. Okay, but just show it to them, and they will like probably like think that this is some wizard level mathematics or something. But like through this video you have like understood it very easily, right? Very simply, that we have understood it step by step. First doing this operation, then doing this operation, then doing this operation, and then doing this full operation, and what each of this means. We have like covered it fully. Okay, so I hope now that is this uh, attention self attention mechanism is very much clear to you. Okay, I hope that it is very much clear to you, and if you have any doubts in any of the topics till now, you can for sure comment it. So now we will move to the next part. Okay, so now we are going to talk about multi-ed attention. Okay, so before that we spoke about self attention, right? We now know that what self attention is. Okay, but in the very start of the video I had mentioned, just let me go through that part. Yes, we have mentioned that the need for transformers, like right, in the need for transformers I had mentioned that there was already something known as the attention mechanism that we just now understood. Okay, but why was it not enough? Okay, because you see this process of doing that self attention, it will take a lot of time. Because let's say that if not just 10 words, instead of just having 10 words, I'm passing an entire essay of, let's say, 100,000 words, 1 lakh words, right? So processing 1 lakh words, doing that particular thing, it will take a lot of time, because I'm going to compare each word with each other word. So basically, just to do a little bit math over here, let's just say I if okay, okay, there was some issue with that. Okay, no problem. Okay, 3 2 1 go. Okay, there was some issue, sorry about that, but we will continue. Okay, so let's just do a very small math over here. If I have 10 words, right? If I have just 10 words, then just imagine that how many comparisons or how many this loop of self attention will occur. For the first word, it is going to be 10 times. The second word, it is going to be 10 times, because it is comparing it with all the words itself included also, right? So for each word, it is 10. For 10 of them, it will be how much? 10 into 10, 100, right? So if I have something like 100,000 words, so it will need these many. Okay, so it will be like a very, very huge number, right? 1 2 1 2 3. So it is how much? It is 10 billion. Okay, it is 10 billion. So just think about that. 10 billion comparisons, it is going to be taking a lot of time. So of course, this attention mechanism, this self attention mechanism, could not handle parallel processing, and we are processing all of these in a single chain, in a single loop. So that's why it is not scalable. We need something which is scalable, which can be used by millions of people, just like now with ChatGPT and Gemini and Claude. Okay, that's where transformers came in, right? We have learned all this, okay, in the start, but I'm just revisiting this part so that each and every part of the video goes stuck in your brain. Okay, so what is the property of transformers that makes them actually parallel? That is what we are talking about. Okay, that is what multi-head attention comes to. Okay, comes to save us, comes for basically parallel processing. Okay, the word multi might give you a hint. Okay, we're doing something which is multi. Okay, and we are doing attention. So basically we are giving attention to that particular whatever the sequence of the text is, multiple attention. And what does this mean? Okay, let's cover that. Okay, so these give the transformer the power of parallel processing by running multiple self attention blocks at the same time. Very simple, very simple. Okay, so what do we have? So like we have learned this earlier, that we take the v, k and q, and then basically do a dot product and lots of things, just like over here. Okay, and then we basically get the final attention score. Okay, so what we are doing in multi-head attention is basically, just instead of running this at self attention, this self attention thing just once, we are basically running it multiple times, multiple blocks of that particular self attention at the same time. So what is happening is that basically we are getting different attentions, different attention scores, and at the end we are just concatenating them. So what is happening is that basically you can think of this way. Okay, like I have written this over here also. This is very important document. You can think of each of the self attention block to capture different contexts of the sentence. Okay, it is like a jury who present different opinions, and then a final verdict is taken after considering all the opinions. Very nice analogy for understanding this, for understanding multi-head attention. Very easy to understand analogy. Okay, basically you must have seen a jury, right? In a jury, basically what happens is the jury listens to the case throughout the case, and then at the end, when the judge basically makes a decision whether the person is guilty or not, basically the judge is not does not have the full power of providing that decision, right? Basically the jury provide their own opinions, like okay, one member of the jury might think that this person is guilty, the other might think that he is not guilty because of some other different reasons. Then after presenting all of the jury's opinion, the judge makes the final decision based on what he thinks from all those opinions. Okay, so that is what happening over here also. Basically we are running different blocks of self attention, and each of the self attention block is paying attention to different contexts. Okay, like one attention block might be seeing that okay,
I am responsible for handling the grammar part. I am responsible for handling, let's say, the verbs and the nouns part. I'm like responsible for handling the creative part, like random things that I can think of. Okay, you can think of that way. Okay, so what is that? We are running self attentions, like different blocks, and they capture different contexts of the sentence. Okay, why is this very important? Because this gives us parallel processing. Okay, which before this we did not have. So multi-head attention is a very like crucial thing that transformers introduced. Okay, and it is very much faster as compared to self attention, because in this we can have multiple self attention blocks, and we can basically like take advantage of those multiple self attention blocks, because taking the concatenation of all those blocks gives us a much deeper and much broader understanding of the sentence of each word. Like it gives us a much more broader, and it does not like just you can say like it does not give like boundary to just one understanding. We are getting multiple understanding of the same thing. So it is like considering all the opinions. Okay, and then taking the final verdict. Okay, that basically this should be the okay. I had this and this and this understanding. Okay, if I combine this, I get this final understanding, and that is what is happening in multi-attention. Okay, this is another page illustrated transformer. It is a very famous website created by this guy, and he has even converted this particular page into a full-fledged book also. And this is a very famous one for learning transformers. It has a lot of illustrations also. So as you can see, this is a very nice looking one. So we have the attention weights of Q, K, and V for this one, and then for the second block. So basically, this is one single attention block, one single self attention block. This is another one, and this is another one, right? So for this one, we have these weights for the Q, K, and V. Then we have these Q, K, and V, and then we do all the operations, and then we finally get the attention score, which is Z0, and then we have Z1, and then let's say Z7. We have these, and then we have a final like weight in which we pass all of this, and then we get the final, very final attention score. Okay, and that is the final one. Okay, so this is how multi-head attention occurs. Now if you ask me, like, why do we have this particular weight? This is important because we want to see like we want to like learn to weigh each of the attention blocks. Okay, we can't give very much attention, very much weight to a particular attention block, right? We need to have understanding of which attention block is providing us more information or less information, and based on that we will judge on that basis that this particular let's say this particular attention block is giving us more information, so I'm going to weigh it more, I'm going to include it more in my final attention score. Okay, and if this one is giving me less information, it is not that important, so I'm going to include it less in my final attention score, and that is what this weight is used for. Okay, so I hope now that you understand multi-head attention, and I hope that now you have also understood everything about self attention, right? You must have understood now self attention, what is self attention, what is query, what is key, what is value. We have went through multiple examples of them, and we went through the whole formula of that. We have also went through multi-head attention. Now I hope that now you understand what is multi-head attention, and now you understand, I think you understand the context of this. Okay, so now we are going to move to the next topic.
So next up we are going to talk about residuals and normalization. Okay, so we are very near to the end of the video, to end of all of the like concepts. So let's stick around. Okay, so let's not talk about residuals and normalization. Okay, so first of all, let us just read the definition out. I have written this for you, and it is the simplest out there, because if you search it on Google or anywhere else, you will get something like more complicated or something else. So let's first read this out. Okay, what is residual? A residual connection adds the input of a layer or block directly to its output, which helps us solve vanishing gradient problem in very deep neural networks. It is like skipping a connection. Okay, so what is a residual connection? There are a lot of jargons over here that you might not be understanding. So let's go step by step. Let's just first try to understand this part. Okay, that a residual connection adds the input of a layer or block directly to its output. Let's just try to understand this. Okay, let's take an example of a function. Let's say I have a function f of x. Okay, so whenever I pass x to this function, it gives me some value. Let's say that is y. Okay, now this f of x does what? It takes some value x, and basically it manipulates the value here and there, and it could do anything it wants with this particular x, and then it returns something which is y. Okay, this is our output. Okay, now what is a residual connection? It adds the input of a layer or a block or a function directly to its output. Okay, so what we are doing is basically I have this x as the input, right? I have this y as the output. Now what if, like, I have this input x and I am getting this y? So instead of having going through this f of x, can I just connect this and this? Yes, I can do something like that. I can basically take another instance of x and just pass this over here, and now my total new output will be what? It will be x plus y, correct? Because now I am getting this x as f of x, that is y, and I'm also getting x as its original form. So it is what? It is now x plus y. So this is my new output. So the thing here you will see this purple color connection. This is what a residual connection is. Okay, so what it does is basically it connects the input with the final output. Okay, it basically skips this, basically it skips this particular function, and this function you can replace it with a layer of the neural network also, or you can replace it with the block of a neural network also. This can be anything, but in the very core, at the very core, it is just a function, right? So that is what a residual connection is. A residual connection adds the input of a layer or block or function. Okay, what is this? This is basically a function. Okay, nothing more, very simple. This is just a function directly to its output. Okay, we understood, at least this part we have understood, that a residual connection adds the input of a layer or block directly to its output. Now let us see which helps us solve vanishing gradient problem in very deep neural networks. Now we see another new term over here, which is vanishing gradient problem. Now let us discuss that. So in order to discuss that, I have another like empty slide, because this vanishing gradient problem might take some time. Okay, so let's try to understand it, that what is this vanishing gradient problem. Okay, so as the name suggests, you can understand that it is a problem, right? It is not some solution that we are using, it is not some concept that we are using, it is some problem that we need to get rid of, and for that we are using residual connection. Okay, now I'm going to make it very crystal clear that what is vanishing gradient problem and why do like residual connection helps us to solve it. Okay, so just imagine a neural network like this. Okay, let's take the example of a neural network something like this. Okay, I have this, I have this and this, and I have this and this. This goes to all three of them. This also goes, just a second, yes, it goes to this and this, and let's say all three of them combine, and this is basically my output. And here I have my input, and here I have my output. Okay, now let's just say that the output that I'm getting, that is, let's say, y dash. Okay, and the inputs that I'm giving, that is, let's say, a and b. Okay, and the weights of these particular neurons over here you see. Okay, that's why I must have like mentioned in the start of the video that you should be knowing at least somewhat about neural networks, because that will help throughout this video. Okay, but still I'll try to make it some more clarity. Like each of these neurons that you see, they have some kind of weight associated with them. Okay, so for example, let's say this is W1, this is W2, weight 3, weight 4, weight 5, and weight 6. Okay, nice and simple. Now we have this very simple neural network to us. We have 6 neurons in this and 3 layers, right? First layer, second layer, third layer. Okay, and we have 2 inputs. We have A and B as inputs, and we have the output, which is y dash. Now why I have this y? Because as you must be knowing that this neural network does not like predict always the right thing. Okay, it might be little off by the actual value. So what I'm doing is that the actual value I'm taking it as y. Okay, so y dash is actually what I'm getting as the output, but the actual original, like the correct value, is y. Okay, now why is this y and y dash different? Because just like I told, the neural network can't predict it 100%. Okay, now we also need this to calculate the loss, right? Because loss is what? I can just calculate the loss as y minus y dash, and I can take the absolute value of this. Correct. Now why is this like very important to us? Because the loss is the thing that we need to minimize so that our neural network can basically become very efficient, like very accurate in like predicting the output. Correct. That is what our goal in building a neural network is. Basically what we do is basically we feed in a lot of data, and for each of those y dash we have the y which is the correct value, and then we calculate the loss, and then we basically make some changes in these weights so that the next time when I try to pass the same values, the loss is much lower. Okay, and so that when I'm like testing this neural network, the loss is very less and the accuracy is very high. Okay, so that's what the goal of building a neural network is. Now how do I basically change these particular weights, the value of these particular weights? How do I change that? Now for that we have a very powerful algorithm which is known as back propagation. Okay, it is a very powerful algorithm known as back propagation. Okay, and back propagation is powerful because it is like it does the job that we need. It can very easily like change the weight values, and it is like very simple to apply also. if even if you don't know what is back propagation, and it can be like easily understood. Okay, and it is also one of the like most uh, important algorithms in machine learning, in deep learning, because neural networks cannot be like built without back propagation. Okay, so it is that important. So just pay attention to this. Okay, so what does back propagation do is, as the name suggests, let's try to break it into two parts. Okay, I have two parts over here. I have back over here and I have propagation. Okay, just a second, let me color that with. Okay, so there was some issue with the there was some technical issue, so I had to like redraw all of this, and I'm like trying to explain all of this in some other application, so just bear with me. So where we were talking about back propagation. Okay, so let us now like look into what is exactly back propagation and how it works. Okay, so let me write that again. The loss that I calculated, it was basically the right value that I have is y, and the value that I'm getting is y dash, and I'm taking the absolute value of this, correct? Okay, now let's see that how back propagation actually works. Okay, and let me just explain it over here only. Yes, so I have these neurons, right? I have just a second. I have this W1, W2, W3, W4, W5, and W6, right? Now, what does back propagation does is that, just like the name, it is breakdown. Let us break down into two parts, back and propagation, right? So by the back, what it means is that you are doing something in the back direction. Okay, like the thing that we did in order to get this particular y dash value, how did we do it is basically we took this a and this b and we passed it to these neurons. Okay, and then these neurons gave out some value, outputted some value, and then it was passed to this, and then to this, and then to this, right? Then what happened is that those neurons further like travel that value to the other neurons, and then we finally got the y dash value. Okay, and then we calculated the loss. Now this whole process is known something as feed forward. Feed forward propagation. Okay, this is what this is, feed forward propagation, or you can even remove the feed word. Okay, it is okay if you just use forward propagation. Okay, so this is what forward propagation is. Now just the opposite of it is back propagation. Now, as the name suggests, it is just the opposite of it. Now in forward propagation, what did we saw? We saw propagation of the values of the inputs through this network, like in this direction. Okay, so what happens is that forward propagation is this direction, and the opposite of it is back propagation in this direction. Now how it works is basically you take this loss and you just like basically you take the like the gradient of this loss with respect to the this particular weight. Okay, and then basically you see that whatever value it is coming, is it coming maybe 0 or some positive value or negative value or whatever value it is coming. Okay, you just look into that particular gradient and then you make the decision that okay, does this particular neurons weight requires some changing or not, and if yes, then you probably change the weight value a little bit, or whatever that basically that is something known as learning rate. Okay, learning rate, because like what learning rate means is basically how much change you are doing to this particular neuron. Okay, That is what is learning rate. So based on this particular loss gradient with respect to the weight, you do the change to the weights value. Okay, now what you do next is basically you take this gradient. Okay, you take you take this particular gradient that you have, and then you basically just do it like number of times till you reach the last neurons. Okay, so what do you do is basically you have like calculated the gradient of the loss with respect to this. Now what you need to do, you just need to calculate the gradient of this with respect to this, with respect to this, and with respect to this, right? Then what you need to do is you need to calculate the gradient of this with respect to this. You need to calculate the gradient of this with respect to this. Then a lot of them. Okay, so what is happening is that basically you are calculating gradient with like gradient of the like current layer with respect to previous layers. Okay, that is what you are doing. Okay, and what you are doing is that you are just back propagating this loss, and that is what back propagation means. Okay, that is what back propagation means. Okay, now what is the problem in this? Now if it's a like very small neural network like this, then it is not a problem. Okay, but what if the neural network is very huge? In that case what happens is that, let's say that if I want to like let's say that instead of 6 weights over here, I have something like 100 layers. Okay, in that case what happens is that if I want to like calculate how much is the gradient, like how much not gradient, let's just say that how much should my first weight of like my first neuron should be changed in order to reduce the loss. So like how do I calculate this? Okay, so for the calculation of like this, you need to do something known as chain rule. Okay, it is a mathematics concept, it is a algebraic concept. Okay, like if you see, what happens is basically you do something like if there is a function in terms of x, and there is a function in terms of t, but it also has some terms in terms of like x, then when you are basically differentiating or let's just say that let's just take a simpler example. Okay, let's say that you have a function which is fx, so it is in terms of x. You have a function t which is in terms of just like that t, and you have a function which is in terms of x and t, right? And let's say I'm denoting that function as y. So if you want to basically calculate the gradient of y, so how can you do it is basically, if you want to calculate the gradient of y with respect to t, then you what do you need to do is basically you need to do something. Just a second. So basically what you need to do is you do something like this. Correct? Is that correct? Because you do something like this only. Okay, you must have uh, like learned this in your 11th or 12th grade maybe. So this is what the chain rule is. Okay, so what is happening is that, let's say I want to calculate the gradient of the first layer, and there are 100 layers. So in that case what happens is that it will be something like this. Okay, let's say layer 1. So what will happen is it will be like this, layer 2 with respect to layer 3, and then this will probably just go on. Okay, so now I think that you must have like got that why is this a problem. Okay, let me give you a hint. Okay, the problem is that on each of these neurons there are some activations. Okay, there are some functions which are also known as activations. These are some of these activations are like tan h, or maybe sigmoid, okay, or maybe some sine value, maybe some cos, or there is also more activations like relu, leaky relu, a lot of activations. Okay, now what these activations are basically, they are just, you can say they are just like very simple functions, right? What this sigmoid function does is that it basically makes sure that the value is always like positive and negative. Okay, and there are a lot of functions like that also. Now what happens is that most of these functions return values less than 1. Okay, so why is that a problem? Now just think about that. When I am basically calculating the gradient, okay, so my value will be somewhere less than 0, somewhere less than 1. So what happens is that for a like a very huge network of 100 layers, so I'm just like multiplying 0 point, maybe let's say 6, then 3, then 0.2, and so on, so on, so on. So as you can see that basically what is happening is that this number will be very less if I have a lot of layers. Okay, because if you multiply something like this for a very like numerous time, then the number will be very small. Okay, it will be somewhere around 0. Okay, so this is where the problem of vanishing gradient occurs. Okay, now as you can see that basically what is happening is that by the time you reach the first neuron, the gradient is vanishing. Okay, and that is the problem. Because why is it a problem is that if it's basically, if this gradient is very less, then there will be very less update to this particular weight. Okay, and if it has very less change in its weight, then it will not be able to give very accurate results. Okay, and that will be a very big problem because it will cause a lot of inaccurate results. So that is why we need some way to solve this problem of vanishing gradient problem. Okay, now let us see that how can we use residual connection to do this. Okay, let's see that. Okay, let's take a very simple example. Okay, let's say that I have a function which is, let's say, sin x. Okay, and this sin x, let's say I'm basically taking the basically, let's say I'm just differentiating it with respect to x. So what do I get? I get cos x, right? Now I'm getting cos x, right? Now what happens is, like, what if I need to calculate the gradient at some particular value? Like what if I want to calculate f of x at, let's say, 30 degrees. Okay, then what it will be is, it will be basically cos 30 degrees. Okay, and basically cos 30 is how much? It is 0.15, right? Now as you can see, the output of this basically the output of this different like the gradient that we did on this particular function, it is less than 1, right? Now what do I need? In order to solve this issue, I need something that so that basically these values become more than 1. Why do I want that? Because if these values are more than 1, they are something like this, let's say, then it will be nice because it will be now greater than 0 and it will be greater than 1 and it will be like some substantial value, right? Correct. Okay, so how do I ensure that? I can do something like that. Instead of this 0.6, I can write 1.6. Then instead of 0.3, I can write 1.3. Instead of 0.2, I can write 1.2 and so on. That is a very nice solution. But how do I ensure that I do this plus 1 in all of this? So how do I do this plus 1 in all of this? So we have a solution for that. Let's say we have something like this only, that the output is coming as less than 1. So how do I ensure that basically I add plus 1 to this? Okay, how do I do that basically? Okay, just a second. Yeah, so how do I basically make sure that it is more than 1? How do I add a plus 1 to this? So let's look into that. Let's say that I do a residual connection to this f of x. So how do I do f of x residual connection? Basically I have this f of, just a second. Yeah, I have this, no, just a second. I have this f of x as sin x and I want some basically residual connection, right? From x it is going to f of x and then I'm getting this output, but I can basically have this x over here and I'm just adding it. So my new output will be x plus sin x, right? Now if I basically calculate the gradient, what it will be? It will be 1 plus cos x. And now if I basically calculate at that particular one, at particular like 30 degree, then it will be what? It will be 1.5. As you can see, our goal has been achieved. We have somehow been able to add 1 to it. Now how is that possible? Is because you are adding the same input to the output and you are differentiating this whole with respect to x. You are calculating the gradient with respect to x, so this value will always be 1 after calculating the gradient. Okay, and why is that? Because it is being calculated the gradient with itself only, so that is why you will always get a plus 1 over here. And that is why it doesn't matter how much less your value is, for sure it will be positive, but it doesn't matter that how much closer it is to 0, it will always be greater than 1. And that is why we use residual connection to solve the vanishing gradient problem. Okay, so I hope now that you have got an understanding of what this gradient vanishing gradient problem is and how we used residual connection to solve it. Okay, so now let's move on to the next topic. So now I hope that you have understood that what is a residual connection, okay, and how it helps us to solve vanishing gradient problem, and what do I mean by very deep neural networks. Okay, so I hope that the residual connection is very much clear to you. So let us read the definition once more so that you can basically kind of revise all the concepts we just went through. So a residual connection adds the input of a layer or block directly to its output, which helps us solve vanishing gradient problem in very deep neural networks. It is like skipping a connection. Okay, okay, done. Now we have done a residual connection. Now it is time to move to normalization. Okay, normalization is also very simple. We can do it very easily. Okay, now let us read the definition first. Normalization is a technique used in machine learning to normalize the data distribution in order to prevent internal covariate shift. In a transformer, we use layer normalization. Okay, now what is normalization? Let's understand it part by part. It is a technique used in machine learning. Okay, there are a lot of techniques used in machine learning. There is this residual connection that we use, and why is it used? To solve vanishing gradient problem. Now there is another problem which is known as internal covariate shift, and we need some way to like get rid of that problem, and that method is what? Normalization. And let's understand that what is internal covariate shift and what is basically this normalization technique and how is it helping that. Okay, let us try to understand over here. Okay, I'm going to like give you a very simple analogy of internal covariate shift. Okay, let us try to understand internal covariate shift. Okay, now what is this internal covariate shift? Have you ever like in your childhood you must have like played the game Chinese Whisper? Okay, you must have like played that game Chinese Whisper. In that basically let's say this here is a person and there is another person and there is another person and there is this fourth person. Okay, there is a group of 4 people, and how the game is played, if you don't know, is basically this first person, second, third, fourth. So what happens is that this first person over here is he basically says something to the ears of the second person. He basically whispers something, and basically the second person basically changes that word somehow. Okay, so what happens is that basically that second person makes some changes to what the first person told him. Okay, and then he says that to the third person, and the third person does the same and then says it to the fourth person, and then the fourth person has to like tell the word that he heard from the third person, or he can even change it. So that is how this game of Chinese Whisper is played. Okay, and no one actually can guess that who actually like changed the word or who actually said the correct word, because if you have a lot of people in this game, it is not easy to guess that where did the word actually like went wrong. Okay, so this is how the game of Chinese Whisper is played. Okay, so very like briefly what is happening is that there are a group of people, and each person basically what he does is basically he changes the input that he got, and in the output he says something else. Okay, so the input for this person changes very quickly. Okay, in the next round it will be something else, and like that. Okay, so this person is basically responsible for changing the word, right? And if you see, internal covariate shift is something like that only. Okay, let me make you understand this. Okay, let's say we take the example of that neural network just like we had, and this time I'm not going to be like okay, just draw, let's just draw it completely only. Okay, this is the this here over is the input layer, this is the hidden layer, and this is the output layer. So we have this neuron. Okay, now let's just let me add just 2 more like let me add this also to make it just a little bit more, you can say, complicated. Okay, let's just say that I have this particular neural network. In that basically I have this input layer and I have this hidden layer, and there are a lot of like layers inside this hidden layer, and then I have this output layer. Okay, now what is happening is that let's take this particular layer out. Okay, let's just consider this particular layer. Okay, now for this particular layer, as you can see, there are two layers behind this. Okay, but for this particular layer, do you think that it will consider both of these as separate like layers? No, right? Because this layer does not know about this layer, correct? It only knows about this layer. So what is happening is that this layer will pass its values to this layer, and then it will basically, these particular neurons will pass some value of their own. Okay, so basically what is happening is that this particular layer is basically changing what this layer was originally passing, something like in the Chinese whisper only, that let's assume that this is the first layer, this is the third layer. So the third layer is not getting what the first layer sent, because the second layer actually changed it. Okay, and why is this like kind of a problem? Like, okay, that is a good thing, because that's what we want each of the layer to basically change the value a little bit until the output, so that we get some valuable output. But why is this a problem also? Okay, what the problem is, that this layer, what is happening is that every time, let's say, whatever input it is getting, it is like the distribution of the input is changing a lot. Okay, now why is that? Basically, first of all, the inputs might be in the ranges of, let's say, hundreds, and then the input might be in the ranges of, let's say, 20s, or the next time it will be in the ranges of 300s. So what is happening is that this particular layer is not very steady with the inputs. The inputs are not steady, they are very like ranging from a very small values to very large values. So we need to have some kind of stability. Okay, so what do? We normalize the values passed to this particular neuron, passed to this particular layer, so that what happens is that basically the values that we are passing to this, they are of a normal distribution. And a normal distribution is that basically what is happening, that the distribution is normally uh, distributed. And why is that? Basically the values will not be very like to the extents to the boundaries. It will be in the normal range, okay, as the name suggests. Okay, so I hope that you understood that what is this internal covariate shift. So basically internal covariate shift is like each layer is getting some kind of input, and what is happening is that the input basically this layer has the input as the okay, let's just let's just back off a little bit. Okay, for this particular layer we have these two as the input. Okay, what is happening is the output of these two layers is acting as the input of this layer. The output of these three layers will be acting as the input of this layer, right? So basically what is happening is that like there is some activations going over here, so there is some changes in the values. So every time I am passing these values to this particular layer, or even this layer, or even this layer, the distribution of the input are changing. So that may cause the layer to have uncertainty about the inputs, and that will cause inaccuracy in the model. Okay, so that is what internal covariate shift is. And the solution for this is basically we normalize the values. Okay, that is what normalization is. I have over here a very like simple graph over here also. So if we see the unnormalized data, it looks something like this. Okay, as you can see, it is extended too much over here and it is extended very less over here, and a normalized distribution is looking something like this. Okay, there is another very, you can say, very important benefit of this normalization also. Okay, now we have like understood that what is loss and how we actually train the neural network and all those stuff. So this like graph that you see, the contours over here, they basically represent all the different values. Okay, okay, all the different values of the inputs. If I have a unnormalized distribution like this, and let's say I am somewhere over here. Okay, what is happening is that if I am somewhere over here, and what do I need? I need to go to the middle, because that is where the loss is the least. So how do I go that way? Basically I make some changes, and then basically the basically based on the learning rate and the like how much basically I am changing based on the loss, that is what the learning rate is. So based on that, I will be like traveling across this contour lines, and then somehow I might be able to reach the midpoint. Okay, that is what my goal is, because that is the place where the loss is the least. So how do I go there? So the problem with this unnormalized data is that if, let's say, I make some changes in the this direction, very I need some very huge changes in this direction, but I also like I am very, you can say, bounded by this direction, because in this direction what is happening is that the width of this part is very less but the length is very much. So I can move this side very easily, but I won't be able to move like in this manner very easily. It will be difficult for me. So it will be like very difficult, it will take a lot of steps for me to reach the middle. Why? Because let's say I take a very big step in this direction, so I might go very far. But if I take a very small step in this direction, it won't be like very you can say impactful, because I need to in that case take a lot of steps to reach the middle. Okay, but if I have a normalized data, the thing is that the distance of the width you see over here and the length you see over here, both of them are same. So it is very easy for me to move. Okay, I can move in any direction and how much I want. I am not bounded by this structure. Okay, so what happens is that I can very easily go to the middle point. Okay, that is the like reason that we want normalized data. Okay, so I hope that now you have understood that what normalization is and what residual connections is, and these are very like crucial, because if I go back to the slide, just a second. Yes, not this one. Yes, if I see over here, you can see that I have this add and norm layer. This is basically the, just a second, the add and norm layer is basically what is also known as the residual and normalization layer. Okay, that is what the normalization layer is. Okay, if you can see over here, basically this is the residual connection, right? You can see that I'm passing it here also, but I'm passing it as a residual connection also. That is what the add means, and the normalization is this. Okay, now as you can see, it is used a lot of parts. Okay, let me talk about it just a little bit more. Okay, in normalization we have spoke about in general that what is normalization and what is basically this internal covariate shift. I have not went very deep into what the formula for basically doing the normalization is. Basically for that, just to give you a very brief, you need to like calculate the mean, the standard deviation, and then you basically normalize the data. This layer normalization, and there is another type of normalization which is batch normalization. So the difference between these two is basically in batch, you basically, if you let's say I'm considering these two. Okay, I have some data over here. Okay, okay, so batch normalization, what it does is it takes a batch of these two, then this, and it takes a batch of basically inputs and then normalizes them. But in basically layer normalization, what happens is that it will take all of this together. Okay, that is the difference between layer normalization and batch normalization. Okay, and you can go deep into this if you want. I will make a separate video on this also, because it deserves a separate video on its own. Okay, so I hope that you have understood both residuals and normalization. Okay, so now let's move on to the next topic. Okay, so now we are going to talk about masked attention. Okay, so what is masked attention? Okay, we had earlier talked about self attention and then multi-ed attention, but what is masked attention? So it is not very difficult to understand. It is actually indeed very simple. Okay, let's just first read the definition and then we'll see what is going on over here. It will be very easier. Okay, masked attention is a mechanism used in transformers to make them autoregressive models. Okay, before jumping into what is autoregressive models, let's just go through the whole definition. By ensuring that the current token can have access to only the previous one and not the future ones, hence masking the future tokens. I hope like you must have got a hint about what is masked attention and what the mask over here actually means. Okay, if not, let's cover it piece by piece. Let's first understand that what is this autoregressive models. Okay, so autoregressive models are basically all the particular type of machine learning model in which basically in order to predict some value, you don't know the future ones. Okay, you only have context of the previous values. Okay, so in order to, like, if I'm predicting 1, then 2, then 3, then 4, so when I'm predicting 1, I can't know this. When I'm predicting 2, I can't know this. Okay, when I'm predicting 3, I can't know this, and when I'm 4, I've already predicted all of them, right? So this is what basically masked like this autoregressive models means. Okay, and that is where the definition of masked attention is also hidden. Okay, so basically in order to make the transformer autoregressive model, that's why we use masked attention. Okay, and what do? We basically give access to only the previous tokens and not the future ones, hence masking the future tokens. Okay, let's take the example of this. Okay, the cat sat on the mat. So basically when we are predicting the word neck, the, okay, we only have context of this. Okay, SOS, this is a special token, right? This is a special token. This, what does this mean? It means start of sequence. Okay, when we are predicting cat, we have context of the only. When we predicted sat, we have the cat. For on, we have the cat sat on, the cat sat. For the, we have the cat sat on. And when we were predicting the last word mat, we had the cat sat on the. Okay, so I hope that this masked attention concept is very much clear to you. It is not very difficult. It is indeed a very simple topic. Okay, And there is a small note over here. Okay, I want you to go through it. That during training we use masked attention to hide the future tokens so that it does not cheat while producing the next token. Okay, so during training, basically we already have the whole sequence of word, but what do we do is basically, if let's say I have something like this only, so what do I do is that instead of giving the whole sentence to the model, what do I do is that I just clear out this particular part and just give maybe the first word, and then I let the model predict the next word, and then I give those two words, and then I let the model predict the third word. And for each of the words that it is predicting, I basically compare that with the original word, and then I see how much further like far it is from that particular word. Okay, and I then basically change the particular weights, whatever weights that we talked about. Okay, and then I try to get the next particular word as close as this one. So that is how masked attention is used in training. Okay, and during inference. Okay, what does inference mean? Inference basically means that now the model training has been performed. Okay, you are no longer training the model. Okay, you are just inferring from the model. Okay, now what does this inferring from the model means is that basically you are basically like when you are using ChatGPT, you are not training the model. You are just asking questions from that like particular like pre-trained model. Okay, and then it is basically just doing what it was trained for doing too. Okay, and that is what inference means. Okay, so during inference, masked attention is used to have autoregressive model property that we have already talked about. We have went through this particular example which shows the prediction. Okay, and what kind of context that is does it have. Okay, so I hope that you now understand what is masked attention. Okay, it is indeed very simple. Okay, so I hope now that you understand that we can move on to the next topic. Okay, so now we are going to talk about the feed forward network. Okay, in short, we also call it as FFN. Okay, feed forward network. Okay, feed forward network is actually a neural network. Okay, if you know what is a neural network, I mean, throughout this video, I have spoke about a lot of concepts related to neural networks, when we were looking into the vanishing gradient problem, or when we were even talking about the attention mechanism and all of that. We were talking about a lot of neural network related stuff. Okay, but till now you must have seen that we have not yet encountered any sort of neural network till now. Okay, till now what we are doing is basically just doing some matrix multiplication and a lot of stuff like that. Okay, right, but neural network also does that to some extent, but it also includes some other stuff also. Okay, so now we are going to introduce a neural network into our transformer architecture. Okay, and that is what we know as feed forward network. Okay, so let's first of all go through the definition. Okay, the FFN is a neural network which is used to provide depth to the transformer and is responsible for all the actual learning of the language. Okay, right, because if you know what a neural network is, or if you have stuck around till this part of the video, you must have got a pretty decent idea about what a neural network is, why do we use it, and basically what type of task we perform with neural networks. We create deep learning models, a lot of them. Okay, before moving to tasks like language tasks, using transformers for these type of language tasks, we were the neural networks was not just used for this. It was also used for building models to predict maybe some kind of disease, or maybe to build CNNs, which is convolutional neural networks, to basically detect whether a person is that same person or not. Okay. And to detect faces, like and a lot of like tasks. Okay. But the sole, you can say the sole basically responsibility of a neural network is to basically like learn any kind of knowledge. Okay. Like any kind of knowledge. Okay. Mostly it is like textual data. Okay. But that textual data is actually indeed like converted into numbers, right? Because neural networks are not good with numbers. Okay. Good with text. Okay. They're like only compatible with numbers, and they're also not compatible with photos and images. The CNNs that we build, they are basically using a lot of, you can say, uh, numeric transformations in the backend. So basically it is numbers at the end. Okay. At the core it is all numbers. Okay. So the actual learning, the point of all of this that I'm trying to explain is that the actual learning of any kind of model happens inside a neural network. Okay. So that is why a FFN is so important in terms of like the transformer architecture. Okay. It might be, you can say, as important as self attention. Okay. Because self attention is the thing that allows us to learn, allows us to not, I would say, actually uh, basically learn those, but through that mechanism we can be like able to learn the basically meaning between those words. But are we okay with just knowing the meaning of the words among themselves? No, right? Because we need to build that like to take that understanding with that we have of the language and then take it further, right? We need to take it further and basically create sentences from it, create essays from it, just like ChatGPT does right now. It does not do just language tasks, right? It has a million other like use cases, right? So for that task we need FFN. Okay. Feed forward network. Okay. Now over here we have been given a very you can say a very theoretical formula of what FFN is doing in the uh, transformer, and this formula is taken from the paper only. So I will break this down, okay, one by one, that what is this basically. And but before that, let's understand what is the use. Okay, I've already like established the use case of this, but just to for the sake of me, just let's read this because I've written this for you guys. FFN allows more information to be captured from the tokens without actually increasing the number of tokens. That is also very important. Okay, in a neural network, basically what you can do is you can upscale or downscale your samples. Okay, if they are images, let's say you must have heard of the terms like okay, this image in is HD quality, it is like in 1920 by 1080p quality, right? You must have heard of these terms, right? That is what the like the number of pixels in the image. So let's say that I'm using the image as 100 by 100 pixels. Okay, but 100 by 100 pixels may not be enough to capture all the information of the image. So I can basically, what I can do is, instead of passing in a very huge image of 1000 by 1000 and saving me some like cost of saving the like storing that big image, or even processing that image, basically, why? Because a 1000 by 1000 pixel image will take more time to process because it is much larger, right? But a 100 by 100 image will not be that much resource intensive. So what I'm going to do, which a neural network allows me to do, is basically let me write it over here. So if I have some 100 by 100 pixel image, so I can basically pass it through one of my neural network layer, and then basically I can like convert it into 500 by 500, or as much as like I can even convert it into 1000 by 1000. So basically what happens that the original image will stay 100 by 100, but I am upscaling it. And I can basically when I am basically outputting my you can say my final output, I can downscale it back to 100 by 100. Okay, that is also valid. So basically neural networks help us, you can say it helps us to work with less number of things also. Even if I have just 100 items, I can expand them to maybe 1,000 and then work with them to get more deeper knowledge, to basically provide more depth into it. Okay, and that is what we were like talking about earlier also, that they are used to provide depth. Okay, and that is why what we are doing is in our case basically what we are having, we have 1200 sorry 512 tokens, right? So these 512 tokens, they are limited, right? We can't pass more tokens than this limit, right? But what we can do is basically we can upscale it to, let's say if we want 1024, we just double it, or we can even let's say 4 times, so 2048. So something like that we can do it, right? Probably yes, it is very much valid. Okay, so that is what we are doing with the ffn. Okay, so what it does, it allows more information to be captured from the tokens without actually increasing the number of tokens. Okay, and it also adds non-linearity to the attention scores, as they are mostly linear, a series of a few matrix multiplications. Okay, let me go much deeper into this. Okay, till now what we have learned about all of this attention score. Okay, let me write it over here. We had learned something that first of all we take q and k, then multiply them, then do a downscaling, right? And then take the softmax of it, right? And then multiply it with v, and this is what my attention score is, right? Now don't you think that value this particular value of the attention score that I am getting, it is just a linear combination. Now what is a linear combination? Let me tell you. Like, let's just say that I have some function. Let me write it over here. I have some function which is x equals to, let's say y. Just a second. I have some function like y equals to x plus 2. Then I have t equals to y plus y square plus 1. Then I have z equals to t minus 5. Okay, let's say that I have something like this. So basically what you are doing is you are taking this x, then putting it in the function of the y, then you are taking y and putting it in the function of t, then you are taking t and then putting it in the function of z. So can you answer this question? Can I write z in terms of x? Is that possible? Yes, it is very much possible. How do I do that? Okay, I will first of all take z, then I know that z is t minus 5, so I've already established that. Okay, then I can basically replace t over here from this t, which is y square plus 1. So I will write what? I will write z equals to t y square. T is basically y square plus 1 and minus 5. So basically I will get what? Y square minus 4, right? Now what I can do is basically I've established it in terms of y, but now I know that y is basically this. So I can do what? I can basically take this y and replace it with x plus 2. So I get x plus 2 whole square minus 4. So then I can basically expand this more if you like. So this will become x square plus 2 2x, yes, because the 4 will get cut. Okay, so I have completed my task of basically representing the value of z in terms of x. So this is what is known as a linear combination, right? Because there is no non-linearity in this. By non-linearity, what I mean is that if you start from a particular point and go to a particular point, then if you can, if you are basically doing a number of like transformations in the like journey, but if you can basically represent the last one in terms of the first one, then it is not a like non-linearity. It does not have any non-linearity. It is what? It is a linear combination. Okay, this is what? This is a linear combination. Okay, so I hope now that you understand what is a linear combination. Okay, now let's understand that why is this a linear combination. Okay, so what all have we established over here? First of all, we have like multiplied q and k, then did a scaling, scale down, right? Then we took the softmax. That is also not basically it is also not a, can say it is not a non-linear function because it is a linear function. Okay, then we have v over here which we are multiplying. That is also not a non-linear function. So at the end of the day, all of these functions like together, that we get the result for attention score, it is a linear combination. Okay, it is a linear combination. And why is it a linear combination? We have understood. I've also written over here that it is just a series of a few matrix multiplications. That is right, because what we are doing is just multiplying this, dividing this, taking the softmax, then multiplying it with another matrix, and that's just it. That's just what our attention score is. So that is just like pure simple math. There is nothing crazy over here. Okay, the thing is that the whole field of deep learning is just pure simple math. I would not say fully simple math, but yeah, it is just purely math. It is nothing more crazy than math. Okay, math is the like you can say the wizard of deep learning. Okay, okay, so back to where we were. Okay, so it is just a series of a few matrix multiplications, or even if we just leave the matrix part away, it is just a like a series of multiplications and some linear functions, right? So it is not non-linear. And why do we need non-linearity in a linear in a neural network? Okay, and neural networks are the one that provide non-linearity. Why do we want non-linearity? The answer is that the thing is, okay, let's just see that what was the linear combination definition that I gave you, that if we go from any point to any point, and we can basically denote that basically first last point in terms of the first point, then we can basically say that it is a linear combination, and there is no you can say there is nothing non-linear about it. But do you think that any kind of learning will be done, any kind of like basically what our purpose is, that we want to learn something like right, we want the transformer to learn the language. Okay, but don't you think that would be just a very huge mathematical expression? But at the end of the day, we can't change anything because it will always be just a single layer actually. Like what I'm trying to say is that I am showing that there are 3 layers over here, but I can just replace this t, right? I can just remove this y and I can directly write this, right? I can just directly write this. So what is the use of having so much parameters, having so much layers? It is of no use, because you can just write that single value in terms of the starting value, right? So we need to have some non-linearity, and for that non-linearity we have a lot of functions, right? Just to like name a few, we have relu, we have another one, leaky relu, we have sigmoid, okay, and there are also other few also, but these are very like you can say used one. Relu is actually even more used, like it might be the most used one for beginners and stuff. Okay, okay, now let's I think I've established the fact that why do we use FFN and what it actually is, and how it actually works and all. I've not exactly talked about the architecture of the FFN, and that's what we are going to talk about now. And before that, let's just be clear that I hope that now you understand that why we are using FFN and what do I mean by non-linearity, and why do we need it, and we have also seen that how neural network helps us to achieve that. Okay, so we have this formula over here that we need to decode, right? So I have uh, like drawn a very simple diagram of this particular you can say this particular formula. This is actually formula indeed, but it can be like sort of it is actually a neural network. It is just in the research paper they are just denoting it as a formula. Okay, so here is this which I have drawn out for you guys. So what we are doing is first we are taking the tokens as x. Okay, over here. Okay, what is x? X is the tokens. Okay, the 512 dimension vector, that is what x is. Then we are passing it through layer 1, in which we have the weight as w1 and the bias as b1. Okay, I think you must be knowing that what is weight and bias, right? Basically, they are linked with each neuron, and they are like used to like control the data of the neuron. Okay, so if I'm like passing any neuron through this, I have a w1 and a b1. If I'm passing x, what I'm going to do, what I'm getting as the output is basically the weight is multiplied and the bias is added. Okay, that is what weight and bias does. So basically what I'm getting is x w1 plus b1, and what I'm doing is I'm adding a non-linearity. Okay, this max function that I'm using, this adds a non-linearity. Okay, this adds a non-linearity. How it does that? Because the max function is non-linear. Okay, it is not linear because you can't actually go back to the starting point because it is not a linear function. Okay, so what this max does is basically we are taking the max of either 0 or this value. So basically what we are doing is basically we are not letting our value to be negative. If what we are doing in this like particular operation, if this value becomes negative, then we are basically setting this whole value as 0. Otherwise, if this value is positive, then we are setting it as that particular value only. Okay, so that is what a linear layer 1. So as you can see, this is a layer 1. Okay, let me write it once again. This over here is our layer 1. Okay, I hope now that you understand layer 1. Okay, now what we are doing is this layer 2. basically what we are doing is we have W2 and B2 in this case. Okay, this is a hidden layer, so it has a lot of neurons, but overall we are in the paper we are just talking about one weight as such. So that is just W2 and just one bias, which is B2. So instead of like representing as 3, you can even think of this as just one neuron also. Okay, but what we are doing in this case is just we are converting this particular 512 dimension vector into 2048 dimension. Okay, okay, now we understand that why we use FFN, and now we also see the use of that, because earlier we have talked about that FFN is a neural network which is used to provide depth to the transformer, and it allows more information to be captured from the tokens without actually increasing the number of tokens, right? So that is what we are doing over here. We are increasing the number of tokens by 4 times without actually, like you can say, actually increasing the number of tokens. Yes, it is like making it 4 times, but the number of tokens that are inputted to this, it is not changing, right? In that way we are getting more information out of these set of neurons. Okay, so that is what this second layer is doing. Okay, and basically if you say if you see, let me just take this, the output of layer 1 is what it is. Basically it is max of 0 and xw1 plus b1. This is the output of the layer 1. Let's just say that I'm denoting as L1. So I'm taking this L1 and then passing it to the second layer. So if I'm just imagining it something like this, passing it to second layer which has W2 as the weight and B2 as the basically as the bias. So what I'm going to get, I'm going to just get L1 into W2 plus B2. So if I'm just going to just a second. So if I'm just okay. So if I'm just going to replace it, replace L1 with the value over here, what will I get? I will get max of 0 x w1 plus b1. Then this is my L1, then multiplied with w2 and plus b2. So this is my output, right? This is my output. Okay, and as you can see, this is what I get over here also. Okay, so I think now that you can understand what is this FFN thing, and what is a neural network and all stuff, and why are we actually using FFN in our case, and how we are basically making like how we are taking the advantage of it. Okay, I hope you understand all of that, right? Okay, so I hope now that we have covered feed forward network. Let's go to the next section. So now we are going to talk about linear layer and softmax. Okay, this is our very last step. This is the very last chapter of our video, and after that it is just we are going to put everything together. Okay, so let's have some patience for just a little bit more time. Okay, okay. So what is a linear layer and softmax? Okay, these are like very simple topics. Okay, let's just go through the definition. It is very much clear. Okay, the final layer that is responsible for converting the raw numeric tokens into words based on a vocabulary which is 30,000 mentioned in the paper. It outputs logits, which are raw output scores for each word. Many new words might be there, like, okay, let's uncover them each by each. Okay, the final layer that is responsible for converting the raw numeric tokens into words, right? Okay, we have talked about a prediction like this. Okay, we had talked about this in masked attention, right? Over here you must have noticed that we were like predicting words, right? We were not predicting some numeric value. Okay, because the user cannot the human cannot understand those words, but for the machine it does make sense for those words. So what we are doing is, in the linear layer we are just taking whatever tokens that we have predicted, and like we are just converting them into words using a vocabulary. And what is that vocabulary? It is like something like this. Okay, it is like for let's say the word max, so I can like just convert it into something like this maybe. Okay, so whenever I encounter this, I am just going to write it as max. Okay, so whenever I get this token in my output, I'm just going to represent it as max. Okay, and how do I basically see that which token means which word, and sort of like that. And you can think of it as a table in which both of like are columns, and you are just seeing that which word means which token, and just referring to that table. Of course it is not like that, but basically that is what known as vocabulary. Okay, that is what known as vocabulary. It is the exact same word that we use in English as vocabulary. Like that means that what number of like different words like you can use in your language. That is exactly what is used in the transformer also. It is basically what number of words the transformer actually knows. Okay, so in our case, in the research paper they have mentioned that they are using a 30,000 vocabulary. Okay, so that is like what they have mentioned in the paper. Okay, so that is what linear layer is responsible for. Okay, converting the raw numeric tokens into words based on a vocabulary. Okay, it outputs logits. This is important, which are raw output scores for each word. So basically, for each of the word, okay, let's just say that I have the input as the cat sat on the. So this is my input, let's say. Now my output should be basically mat. Okay, this is my required output, right? So how do I get this? So basically when I pass this particular sentence to the transformer, it has to somehow like predict that the next word is mat. So how does it do that? So basically there might be a lot of words that basically um the transformer has predicted. The word basically that is next, it can be a lot of other options also. That instead of mat it could be something like bed. It also makes sense. The cat sat on the bed, the cat sat on the table, the cat sat on the chair, the cat sat on the rack, the cat sat on the car. It can be anything, right? It can be a lot and lot of things. It just cannot be mat, right? And we just can't be like putting it as required output. Okay, we can like during training we can like probably pass this and like expect it to return mat, but of course it can be a lot of options also, right? And in our case there are like 30,000 options. Okay, so basically for each of the word there is some like score. Okay, like it could be something like this, that mat has got a score of let's say 12.5. Let's say table table has got a score of, let's say, 20.7, and so on and so on. Okay, that looks a bit ugly. Okay, so on and so on. Okay, so we have a lot of them. So what happens is that for each of the word in the vocabulary, it has generated some score, and this is what is basically known as logits. Okay, and basically this is what the linear layer also does. Okay, it basically sees that, okay, this is the token, and based on that I am giving scores based on like whatever output I have like got. Based on all of that, I am just scoring all of the 30,000 words. Okay, and the scores are known as logits. Okay, now we come to softmax. Okay, softmax is very simple. Okay, we pass the logits from the linear layer on the softmax, that converts them into probabilities that sum up to 1. Probabilities that sum up to 1, that is the exact I think like definition of probabilities, because probabilities always sum up to 1. Okay, it is not something like external property that we have mentioned. I just written it like just for clarification. Okay, so this is the formula for softmax. We will look into it just a bit later, but before that, what we are doing is basically in the softmax, we are just taking these logits, these raw scores that we have, and just passing it to softmax. Okay, and what it will do is it will basically convert this into some kind of percentage. Okay, it will take this basically what it will do is it will take this and convert it into some percentage, like let's say 20%, 30%, and for each of the 30,000 words. Okay, it is going to do that for each of the 30,000 words, for each of the 30,000 logits, right? So what it is doing is it just pass the logits. We are just passing the logits to the softmax, okay, from the linear layer, and the softmax just converts them into probabilities. Okay, so we get in terms of percentage, right? And we have also looked into softmax later down the later like sorry earlier in the video also, during when we were like talking about attention weights, right? So that is the same thing over here also. Okay, so I hope now that you understand both linear layer and softmax. Okay, just to like recap just a very small bit. Okay, so what we are doing is we are getting the final output, and we are just you can say like based on that output we are just giving scores to all of the words in our vocabulary. In our case it is a 30,000 words vocabulary, and for each of those 30,000 words we are assigning 30,000 logits, right? These are the raw scores. Then we pass them to the softmax, and then that softmax takes care of them and converts these raw scores, which are logits, into probabilities, which you can see in terms of probabilities, and then the rest of the like thing works. Okay, I have also mentioned a note for that, basically what happens to the rest of the thing. Okay, so during training what we have, what happens is that we use something known as cross entropy loss on the logits to find the loss and then back propagate that loss for better accuracy. So if you don't know what cross entropy loss is, basically cross entropy loss, just a second, cross entropy loss is basically whatever logits you have got, you're just comparing it with the like actual like desired output. Okay, you can say desired output, and then you just calculate the loss. Okay, so there are a lot of different ways of calculating the loss. So basically cross entropy loss is just one of the ways of calculating the loss. Okay, you don't need to go into the formula of it right now. if you want, you can search it on Google and all. It is very like simple and all. There are a lot of other ways of calculating the loss also, but cross interval loss is a very famous one also. Okay. And the thing is that during training we do not like usually pass it through the softmax layer and then basically predict that what is the next word, present to the user that what is the next word, because we don't want that. Okay, we just want to like calculate the loss and just like back propagate that loss and just like increase the accuracy of the model through the backpropagation algorithm. Okay, we had talked earlier about that, right? But during inference, what happens is just we pick up the top k words where k is the probability for each one. Okay, so during inference, what happens is that we pass them through the softmax, and then what happens is that we get the values of the probabilities, right? And then we take the top k ones. Top k is basically is, you can say, if I'm saying that k is 5, then I'm taking the top 5 words with the highest probability. So that is what top k means. Okay, there are a lot of other ways of like predicting, selecting the next word. The first one is just a principle, a technique known as greedy decoding. Greedy decoding, what it means is basically, I'm just going to write it if you want to learn more about it. So it is known as, sorry, greedy decoding. Okay, greedy decoding, what it means is basically you just take the select the word with the highest probability. That's it, no more fuzz. Okay, and top k is one where you select the k highest probabilities. Okay, that's it. Okay, so that is how the linear layer and the softmax layer works. Okay, I have not gone into this formula, but it is not that important. I'll still explain it to you a little bit because it is mentioned it over here. So basically what we do is we take e to the power z. Okay, and z is, okay, let me just uh, let's take an example, very short one actually. Let's say that I have some logits as maybe 1, 2 and 3, and I want to basically apply softmax to this, so I can basically convert it into percentages, into probabilities. So basically what I do for 1, to convert this into probability, what I do is I just take e to the power which is 1, and then I take e to the power 1 plus e to the power 2 plus e to the power 3, and for 2 what I do is e to the power 2 and the same thing in the denominator. Okay, for 3 what I do, e to the power 3 and the same thing in the denominator. Okay, this is how I get my softmax. Okay, and if you basically, it is a simple math also, like if you add all three of this, what will you get? If I'm just writing it over here, if I add 1, 2 and 3, I will get e to the power 1 plus e to the power 2 plus e to the power 3, and the denominator is common for all of them, and this will get cut and I will get 1. So we have successfully converted them into probabilities, right? So if you just do the math and calculate of this, you will get it in terms of probability. Okay, so this formula might look very like difficult, but it is indeed very simple to understand. Okay, so I hope now that you have understood everything about linear layer and softmax. Okay, so now we have covered everything that is included in our slides about the transformer. Okay, and in short we have covered everything about transformers also in the research paper also. Okay, because I have like tried to keep all of my content as much
you can say like inspired from the research paper also, and also from other resources also. And like I've also mentioned all the resources in the video also. But now it is like time to understand the full big picture. Okay, by now you have understood all of the parts piece by piece. Okay, so now we are going to like put all of that knowledge together to understand that how the transform actually fully functions. Now for like it is now very easy for you to understand the full functioning, because now you already know how each part basically behaves like. So it is like not very difficult for you to do that. So I just want you to do a quick little exercise, that for this diagram that you see over here, just like go through it. Okay, by now you must be knowing what is input embedding, what is output embedding, what is positional encoding. You must be knowing what is multi attention, what is masked multi attention. You must be knowing what is add and norm, right? Add and norm, if you have any kind of doubt, basically we have used residual connection as our term, but it is also sometimes known as add also. So we are like normalizing and doing the residual thing over here also. Then you know, now understand the feed forward network. You this is just the same thing, same thing, same thing, same thing. Then like know by now what is linear layer, what is softmax, and then what the output probability that we have got. So a little exercise for you, like just pause the video right now and just look into this whole diagram, and then just try to build a sense of understanding that what is totally happening as a big picture. Like just see the arrows, that what is happening, and then just try to understand at your own that what is happening. If you can, I would like highly recommend that basically try to do something like just take out a pen and paper and try to draw out things, and basically just try to understand it on yourself, because it will be very helpful. Okay, and then come back to the video to get more clarity, that to see if anywhere you went wrong, or if anywhere like you want more clarity. Okay, so just do that exercise. Okay, and if you have by any chance, if you have a ipad or like uh, any type of tablet with any like stylus or apple pencil, then I highly recommend you to just take this screenshot and then just try to draw upon it. Okay, okay, so I hope you have done that. Okay, now I'm going to just like give you an overview. Okay, like how everything works. Okay, so first of all we have the inputs. Okay, we basically have these inputs in terms of words. Okay, it could be like the cat sat. Okay, something like this. Okay, so we have some words like that. Then we give them as inputs, then we do the embedding. We know what is embedding. Basically we take the text and then convert it into, you can say, vectors, right? Then we are doing positional encoding. Positional encoding is basically like in normal embedding, the words actually the words, the order of the words is actually destroyed, because when we do the embedding, the vectors do not recognize that which word comes first or which word comes later. So we need some kind of positional encoding algorithm. Okay, so that is what we are doing over here. Okay, in our in the research paper they use sine cosine. Okay, then we have what we have multi-head attention. In multi-head attention we have a block, like not just a block, multiple blocks of you can say like self attention blocks, right? In self attention what happens is basically we take one particular word and we take the cue of that word, which is basically a matrix, and we basically multiply it with all of the other words, all of the other k vector of the of all the words. Then
basically why we are doing that is basically we are trying to get the answer to our query for that particular word, and then what we are doing is basically we take the downs we basically downscale that, because that value might be a little bit higher or something. Then we, after doing that, we pass it through the softmax to get the attention weights, and then we basically multiply it with all the value vectors, and that is how we basically get the uh, attention scores. Okay, now why do have next we have this add and norm. Why do we have this? Basically residual connection is helpful because it solves the vanishing gradient problem, because vanishing gradient problem occurs in very deep neural networks, and these are very deep neural networks. Okay, so that's why they are needed. Okay, and normalization is needed because it helps us to converge the loss very fast, and also to like it makes the training much faster also that way, and it also like decreases any inaccuracies. Okay, then we have the feed forward neural network, which is the FFN, feed forward network. Okay, that is just a like simple neural network, like which is used to provide depth to the tokens without actually increasing the number of tokens, right? And like actually it is responsible for doing the actual learning purposes, and actually providing more depth into the what we are trying to learn. Okay, then once again we have add and norm. Okay, now let's try to break the decoder down a little bit. We have the output embeddings. It is the same as the input embeddings. Okay, we just have the outputs with our which are basically you can say the words only, which are like being outputted by the decoder. Okay, we are just going to talk about it in detail just a little bit more later. Okay, then we have the positional encoding. It works the same as this one. Then we have the masked multi-head attention. Why do we have masked over here and not here? Basically in decoder we don't want our word to see the next word during prediction, so that is why we are doing masked multi-head attention. Okay, then we have the same add and norm layer. Then what we are doing is basically we have this multi-head attention. Okay, in here as you can see we are passing like we are passing inputs from the decoder also, from the masked multi-head attention, and from the encoder also. Why is that? Basically in this multi-head attention block is where we are like combining all the knowledge of that, like you can say we are like combining the knowledge of the decoder and the encoder. Okay, like the encoder is basically responsible there is not very much difference between the encoder and the decoder. The decoder has some changes in which basically it has these two layers, and not very much difference, because it is just responsible for like actually outputting the tokens, and the encoder is basically responsible for just building a sense of the training data and not actually like predicting anything. So that is why it is just like building an understanding of it, and we are just combining all of those knowledge from both the encoder and the decoder. Then we are once again adding add and norm. We are normalizing that, and we are having a residual connection just like before. Okay, then we have the feed forward network once again just like this, and then we have the add norm layer, and then we have the linear layer. Okay, in this linear layer we finally like project all of those project that particular output that we get into all of those 30,000 words in our vocabulary. Okay, which was mentioned in the research paper. Okay, then what do we do? Then we basically pass those logits, which are those 30,000 raw scores for each of those 30,000 words, and then basically we pass those through the softmax layer, and then we basically get the probabilities for each of those words in the vocabulary, and that is what known as the output probabilities. And then what we do is basically we can select like if we are doing a technique like greedy decoding or something like that. So in that case, basically what we can do is basically we can just select the word with the highest probability and then just take it and then just in uh, uh, put it in here. Okay, put it over inside the decoder. Okay, so it will work something like if it is like predicting a whole sentence like the cat sat on the mat. So basically if it has successfully predicted that the first word is cat, then I'll probably take the and then pass it over here to here. Then for the next basically you can say for the next loop, for the next prediction actually, the will be also provided as an input. Okay, then for the next input it will be basically for the cat will be actually the next output. So we will basically this time it will be not the, it will be cat. So it will take this and once again go over here, and then it will basically have the cat as the input, and the cycle will go on till it does what, till it recognizes till it basically predicts this end of sequence. Okay, this is a special token which basically denotes that okay, I have like predicted the whole sentence, so predicted the whole sequence. So there is nothing, no more prediction left to do. Okay, so that is what EOS is. And now I hope that you understand the full working of the transformer. Okay, uh, I hope that you understand now the full under architecture of the transformer. Okay, just to make it a bit more simpler, I have drawn a diagram of my own also. It is like you can follow this diagram because this is, you can say, the official one. So if you know this one, it is probably very much better. But you don't have to like draw this also. If you just remember this also, it if this diagram feels a bit jarring to you, you can basically look at this one also. I have kept this also very simple. Okay, and what this basically means is that in the transformer, in the research paper it is mentioned that they have used 6 encoder and 6 decoder. Okay, that's why I have mentioned it over here also, just for your a little extra information. Okay, and I have done some abstraction over here so that you don't have to so to actually make it more simpler actually. Okay, so if you want the raw stuff, you can basically look at it at this one, and I would also recommend you to look at this one. This is just for you to like keep a mind map. Okay, you don't need to like necessarily remember this whole, you can kind of remember this as a mind map and then basically expand on it. Like in the input processing, just remember that okay, when we are processing the input, we are basically first doing the embedding, then we are doing the positional encoding. So just remember that only. I would say that message is important. Okay, I have another diagram also. Okay, this one is taken from this particular page that I have already mentioned in another resource that I have used from this person, and I've also mentioned that he has a book on transformers also. Okay, and this is one is also very simple to understand also. Okay, so you can like you have 3 options to look out for. Okay, either you can basically look at this and try to I would not say like learn this by heart, but just try to draw it on your own. Like even if you draw something like this or even something less than this, it is totally okay. Just try to like you don't, you won't be like asked to draw this whole diagram in any of your interview or anywhere. Okay, it is just for your knowledge purpose. Okay,
because the thing is that this particular transformer architecture is no longer used also. There are multiple changes done. Okay, there are multiple changes. Okay, there is if you want to learn a bit more, I'm recommending another thing. There is a concept known as kv cache. Okay, it is a very nice concept that how it actually you can say like how it actually makes the system more efficient, so you can look into that. Another thing is you must have heard of DeepSeek, right? So I don't exactly remember which one of the models did that, but basically DeepSeek had introduced in some of their model in basically I think it was V3 or something. But basically what they did is in that model basically they had introduced a new kind of architecture which basically had much more efficiency than anything else, like even like better than kv cache or anything, right? And that was like phenomenal. Okay, I will try to like look up that video, and if possible I will provide the link to that video in the description. You can check it out. Okay, so I think now we are done. Okay, so congratulations, guys. Pat yourself on the back if you have covered and stayed till this end of the video. Okay, and it is like really commendable that you have like stayed this long throughout the video and grasped all the concepts. And I hope that you have learned all the concepts very well, and you're always like encouraged to ask any questions in the comment, or even like email me, or any sort of communication that you like. I provided all of my communication methods in my channel, in my description, so you can of course like reach out to me, and I will for sure try to answer. Not even just try, I will for sure answer it. Okay, so don't you worry about your questions being not answered or any sort of that issues. I will for sure answer it. I just hope that you like have got if not 100%, at least 90% of the video you have understood it. And I would recommend you to watch it once more, um, probably in much more higher speed, uh, and just skimming through the video and not just watch it fully, just skimming through the important parts, so that basically um, you can be like having more better understanding of the whole concepts. Okay, so that is it, guys. I hope that you have now successfully understood almost everything that we have uh, I have tried to teach in this particular video. It was a particularly very long video, and I hope that you understood everything. So thank you, guys. Let's meet in another video. Till then, uh, please share this video, because it took a lot of effort, almost 1 month's effort into making this. So please show some love into this video. Please like it, please share and subscribe, and thank you, guys.